computer games often required internal programming for specific video cards and specific sound cards. It was often necessary to go into the settings for each game and tell the game what type of video card you had, what type of sound card you had, for the purpose of configuring the game to use that particular hardware. Imagine if that had to be done for every single application on the system, including, say, a calculator or a web browser. That would be a very untenable situation in terms of being able to make use of computers the way we use them today. Also, what if we could only run one program at a time on a computer system? Years and years ago, that was the case. However, a modern system is running multiple applications simultaneously, and it's up to the operating system to ensure that all these applications can access resources. So each CPU is divided among the different programs. Each program gets access to memory, input-output, as well as disks. Policies that isolate applications from each other, so that a crash in one application doesn't take down the entire system or other applications. Now, of these examples, do we have a situation where we have abstraction or arbitration? Well, first example supporting both Intel and AMD processors. This is an example of abstraction. We don't have to write separate software for an Intel processor relative to an AMD processor, at least for 99.99% of applications. Simply write the application once. Memory allocated to different applications is also an arbitration activity. It keeps one application from overwriting the contents of memory that's being used by another application. Enabling video conferencing software to use different camera devices. This would be an example of abstraction. The video conferencing program just has to know how to use a camera interface that the operating system provides, and then different cameras from different manufacturers can be used without having to write the application, the video conferencing program, to be able to talk to each individual camera. Similarly, accessing two different hard disks from two different manufacturers. Any underlying detail differences between those drives can be handled by using the operating system to abstract away the details. Sending and receiving messages over a network is both abstraction and arbitration. On the one hand, we're abstracting away the details of each particular network card to be able to send and receive the message. On the other hand, we're sharing that network card among all the different applications. Is the middleman, so to speak, between the applications and the libraries and utilities upon which the applications depend and the underlying hardware. Specifically, the core of the operating system, or the kernel, so named after, say, a kernel of corn, is the minimum piece of software that's needed to share the hardware between different applications. Whatever lives outside the kernel that is software is said to be in user space. That means it's application code, or sometimes even parts of the operating system, that are not strictly necessary to share the hardware or abstract away its details. Now, operating systems implement a common mechanism for allowing applications to access the hardware, which is abstraction. And the applications make requests from the operating system to go and access the hardware or other features by making system calls down into the operating system. This is called entering the operating system, or entering the kernel from the top path. Operating systems are also able to alert applications that hardware has changed. Perhaps a network packet has come in. Perhaps the user has pressed a key on the keyboard. These alerts Now, there are a wide variety of operating systems out there. They basically fall into two categories: Microsoft Windows, which is not Unix, and everything else, which is Unix. Microsoft Windows systems, non Unix systems, are the most popular desktop operating systems at the moment. However, they're rapidly being eclipsed by tablet devices, most of which are running Unix style systems. Windows is typically pre-installed by PC manufacturers, which accounts for a good portion of its present popularity. Unix systems, on the other hand, are installed by the end user, except for commercial Unix systems and Mac OS X. Mac OS X is probably the best-selling Unix system of date. And Linux, which includes the Android platform, is probably second. Now, there are some mainframe systems out there also, some of which are Unix-like. Some use custom operating systems. There are a variety of players in the embedded systems market. However, that's presently dominated by Android, with Apple's iOS, which is based on Mac OS X, in close second. Others, Symbian, BlackBerry OS, TinyOS, are designed for smaller markets. Now, the idea behind the Unix system began with time-sharing system started in 1964 called Multics. And the idea behind Multics was to make computing into a remote service to be accessed by terminals using telephone lines. It wasn't terribly successful because dial-up connections at the time, at about 9600 baud, were rather slow. However, Canada actually did have a Multics system deployed and used it as part of their national defense network until the year 2000. Multics is remembered, however, primarily for its influence as a multi-user shared system. And today, with cloud computing, there's some significant parallels between some of the cloud computing models that we use and some of the ideas that were pioneered back in the Multics system. Now, Unix was actually a play on the term Multics. It was developed by Bell Labs in 1969. It's actually a trademark term, so some authors use Starnix to refer to the family of systems and use the word Unix only for the commercial distributions. The original Unix systems were commercial distributions, the free variants BSD and Linux coming along late 80s and early 90s. Unix systems are time-sharing systems in that they support multiple users at the same time, but they're designed to be run on local computer resources instead of remote resources. Berkeley System Distribution, which is based on AT&T's commercial distribution, is one of the first open source Unix systems to emerge. It was based on the commercial distribution, so AT&T sued.
Tita Jel, thank you. Makinig lang kayo dito sa tutorial, ha. Tutulog lang ako.
BSD system. Linux, however, was an alternate approach to getting a Unix-like running on a computer system. This was started by Linus Torvalds as an undergrad at the University of Helsinki, released in source code form in 1991, and often combined with a set of user space, utilities, and libraries created by the GNU project. Thus, the resulting combination is sometimes called GNU/Linux. It has been commercially successful for many device classes, including web servers, network and embedded devices, and mobile phones. Some people, including myself, use Linux as a desktop platform, and it does have the benefit of having one kernel that's scalable from embedded devices all the way up to supercomputers. Valuable tool for us in terms of learning about operating systems. Now, what is Linux? Well, generically, the term Linux refers to a class of operating systems that use a common kernel. Now, distributions of Linux, or operating environments as they're sometimes called, are cobbled together by taking the Linux kernel and adding various different user space tools to it. Many of these core tools originated in the GNU project, which originally started in MIT. Thus, systems are sometimes called GNU/Linux instead of just Linux. I typically, however, say just Linux, referring to either the kernel itself or to the operating system distributions that are based on that kernel. The Linux kernel was originally started as a hobby by an undergraduate at the University of Helsinki, a gentleman by the name of Linus Torvalds. He still heads the kernel development project. Linux is what's called a monolithic kernel, and that means that the device drivers are built into the kernel. However, it's not a true monolithic kernel because the device drivers can be built as modules and loaded and unloaded from the kernel at runtime. The latest stable version was 2.6.37 on January 5th, 2011. That has since been updated to version 3.03, I believe, was the latest version that I've seen as of now, which is late August 2011. The latest version can also be checked by going to www.kernel.org. Here is an example of some of the main components of the Linux operating system. At the lowest layer, we have computer hardware. On top of that hardware, we have the Linux kernel. The Linux kernel contains a number of built-in subsystems that enable access to computer hardware. These include drivers, memory management, process management, file systems, networking, including sockets and protocols, and other utilities that the kernel provides. On top of the kernel, we have the GNU C library, upon which most other libraries are based, since C is typically the lowest level system language to which all other software is eventually compiled. On top of that, we have our compiler, GCC, some important utilities called core utils, also part of the GNU project, and the born-again shell, or bash, which provides a command line interface into the system. All we need in order to run a Linux system and do useful things with it is everything below this line where I'm moving the mouse right here. All the software above this line is add-on software that's not strictly needed in order to run a Linux system, but makes Linux systems more convenient or do other things. So for example, we can add network tools such as Secure Shell Server and a generic services server called inetd that can launch all kinds of different services. We can also run a LAMP stack that stands for Linux, Apache, MySQL, PHP. If we're in a desktop scenario, we can also run a graphic user interface. This includes X11, specifically the X.org distribution, and one of a number of different environments that can be run inside X11. Popular ones include GNOME, KDE, and XFCE, which isn't on this particular graphic. Now, a large number of people have come up with different distributions of Linux. These distributions contain different sets of software, but they all share the Linux kernel in common. We typically classify distributions by which package manager they use. Unlike Windows and Mac systems, where we install individual applications and then have to manually update each application by running separate installers, Linux distributions typically use package managers, which download and install extra software and update existing software with a single command. These package managers include the Red Hat Package Manager, or RPM, which is used in Red Hat Enterprise Linux, Fedora, Mandriva, OpenSUSE, and a number of other distributions. A competing package format is the Advanced Package Tool. This is used primarily by Debian and derivatives of Debian, such as Ubuntu. There are other binary formats, however, in use. Slackware uses a TGZ format with its own package management units. Arch Linux has a custom written package manager called Pacman, and there are some others out there. There are also source formats. Gen 2 is able to build everything from source using ebuilds. Linux from scratch isn't so much a distribution as it is a book that tells you how to put together your own Linux system by compiling sources for each particular application. This is, of course, time consuming. And there are other source formats out there as well. Now, in industry, Red Hat Enterprise Linux is quite popular. It's a Linux distribution from Red Hat Incorporated, which is based in Research Triangle Park, North Carolina. That's in the Durham area. It is an open source distribution, but the official product is sold with an update subscription accessed via per installation serial numbers. Therefore, in order to get the update subscription and the installation media, it's necessary to purchase the subscription from Red Hat. They do use the RPM package format. In fact, they invented it. RPM stands for Red Hat Package Format. CentOS is a free rebuild of Red Hat Enterprise Linux that's widely used in academia, industry, on many high-performance computing systems, and for many other applications. This, of course, uses the RPM package format and is available at zero cost. Fedora Core is a community distribution that's sponsored by Red Hat that grew out of an old product that Red Hat used to produce, which was called Red Hat Linux without the enterprise part. And Fedora is used to develop and test packages and infrastructure that are later incorporated into the enterprise Linux product. Debian is a fully open source distribution which avoids proprietary software and has an emphasis on security and stability. The stable version of Debian is extremely stable because the packages are extremely well tested. The flip side is that those packages tend to be rather dated, and thus an unstable version is available if more bleeding edge packages are needed. Debian uses something called the Advanced Package Tool, or APT, in order to manage its software. Ubuntu is actually based on Debian. It's sponsored by a company called Canonical Limited, which is based in South Africa. It's designed to be easy to use and friendly to new users switching from competing platforms. There's a new release every 6 months, and it's often necessary to completely reinstall the operating system at each new release. There is a functionality that's built into the Advanced Packaging Tool called Disk Upgrade, which seems like a great idea on paper, but in practice often doesn't work right and leaves the system unstable. Ubuntu also has a package pinning policy. Thus, once a package is released, it's only updated for security updates. If new features are added, one has to wait till the next version of Ubuntu comes out before getting the newly updated package. Now, Arch Linux, which is what I personally run, is a minimalist framework for creating a custom system. It's not so much as a distribution as it is a set of tools that enables each individual to create his or her own installation, customized to his or her own desires. It's a different philosophy from traditional distributions. It is a completely written from scratch distribution. It's not based on any other, and it is what's called a rolling distribution. There are not discrete versions of Arch Linux. Every time you run a system update on Arch Linux, you get the latest version of the operating system, along with the latest version of all application packages and all the latest bugs. And Pacman Package Manager, which was written from scratch for Arch Linux, is used to manage the software. So these are just a few examples of different Linux systems different Linux distributions that can be used with a highly scalable Linux kernel. A hard disk drive for access by multiple programs. In particular, I'll talk about disk attachment, talk about some of the properties of magnetic disks, discuss disk addressing, discuss partitioning, and introduce solid-state drives. I'll begin with disk attachment. Disks are attached to the motherboard via some kind of cable, and the exact type of cable depends upon the bus in use on the system. There are several different types of bus, which are implemented by different chips attached to the motherboard on the different computer systems. One common bus that was widely in use until the early 2000s on consumer-grade hardware was the Integrated Drive Electronics, or IDE bus. This has been since backronymed Parallel ATA, or PATA. It consisted of 40 to 80 ribbon cable connecting to a 40-pin connector to provide 40 simultaneous parallel channels of communication between the motherboard and the hard drive. Enterprise-level systems of that time period typically used SCSI, or Small Computer System Interface buses, which consisted of a cabling of 50 to 80 pin connectors between the hard disk and the motherboard. SCSI also defined a standard set of commands, a standard protocol, for interfacing with disks, CDs, and other types of storage devices. This protocol was useful for recordable CD media and DVD-ROM media, and was implemented on the ATA bus using the SCSI protocol in a system known as a TAPI, or ATA Packet Interface. Now, in modern times, serial interfaces between the motherboard and the disk have replaced, for the most part, the parallel interfaces. For ATA-style disks, we have serial ATA, or SATA, which replaces the 40-pin connector with a 7-pin connector. It still uses the same protocol, either ATA or a TAPI protocol. And serial attached SCSI, or SAS, which uses the SCSI protocol over a narrower channel consisting of 26 to 32 pins. Both of these new serial attachment mechanisms support higher bus transfer speeds, enabling theoretically faster devices to be attached to the motherboard. This does not necessarily mean, however, that the disks have gotten that much faster. Now, we still store large amounts of information using magnetic disks. These are metallic or glass platters that are coated in a magnetic surface, and a stack of these platters is rotated at high speed by an electric motor. A stack of heads moves back and forth across the platters, altering the magnetic fields in order to read and write data. Moving the heads back and forth results in seek time, and waiting for the platter to rotate around to the correct position results in rotational delay. Historically, magnetic media were addressed by geometry. The smallest addressable unit of space on a hard disk is called a sector. This is typically 512 bytes, at least on older disks, though other sizes have been used, and newer drives go up to 4 kilobytes. Tracks are circular paths at a constant radius from the center of the disk, and each track is divided into sectors. One head reads from a single track on a single side of each platter. When you stack multiple heads up using multiple tracks on the various sides of several different platters, the result is what's called a cylinder. And historically, accessing disks required accessing the particular data locations using cylinder head sector, or CHS geometry addressing. As disks grew larger and faster, however, this type of addressing scheme became limited, and so logical block addressing was put into use, and it's now the standard today. Logical block addressing, or LBA, gives each block on a disk its own logical address and leaves it up to the disk firmware to convert the logical addresses into physical locations on the disk. Current standards with logical block addressing on ATA will allow enough space for disks up to 128 petabytes. Operating systems normally implement these 48-bit addresses using 64-bit data structures. Thus, operating systems that support 64-bit disk addressing can generally support hard disks up to 8 zebibytes of data, assuming we're using 512-byte sector sizes. Now, regardless of the size of the disk, it is convenient to partition the disk into multiple sections so that we can isolate data from each other. We can isolate the main partition of the operating system from a partition we would use for swapping out pages of virtual memory, for example, and we can isolate that from user data. Also, with early hard drives, it was convenient to isolate partitions so as to minimize seek time by making it such that the head didn't have to move as far in order to access data. Now, there are two types of partition table, or data structure that resides on the disk to indicate where on the disk the different partitions lie. A common partition
Gising
table
ako,
type
gising.
that's in widespread use today is the master boot record-based partitioning scheme. And the way this works is that the BIOS on the system, the basic input-output system, actually loads the first 512-byte sector from the boot drive at boot time, and code stored in that 512-byte sector loads the rest of the system. Also within that sector is stored the partition table, which is called a DOS-style partition table. And the DOS partition table still uses legacy cylinder head sector addressing, supports a maximum of 4 primary partitions, one of which can be an extended partition with logical drives in it, and supports maximum partition sizes and maximum partition starting addresses at 2 tebibytes. This is the default partitioning scheme for Microsoft Windows and most Linux distributions. However, as hard drives become larger and grow past 2 terabytes, the GUID partition table, or GPT, starts to be used. This is a larger partition table that can support disks or partitions up to 8 zebibytes in size. For compatibility with old partitioning tools, to prevent old tools from overwriting sections of the disk and seeing it as free space, a protective or dummy master boot record is retained at the beginning of the disk. GPT is the default partitioning scheme in Mac OS X, is an optional partitioning scheme in Linux, and is supported in 64-bit versions of Windows 7, Windows Vista, and Windows Server 2008, provided that the system uses the Extensible Firmware Interface, or EFI, instead of the legacy BIOS interface. For Linux, the Grub2 bootloader can use a legacy BIOS interface, but requires a dedicated small partition on the hard drive in which to store the rest of the bootloader. Now, hard drives and magnetic media are used for large quantities of space because of their relative low cost. When high performance is required, we prefer to use solid-state drives, or SSDs. These drives have no moving parts, which makes them generally faster and less subject to physical damage than mechanical hard disks. Most of these SSDs use NAND flash memory to store data, and this is a storage mechanism that's based on injecting or removing an electron from a flash cell. Injecting an electron into a flash cell changes its state from 1 to 0, so this is backwards from what one would expect. An empty flash cell actually has a state of 1 instead of 0. The membranes through which this electron is injected and removed eventually wear out, typically after anywhere from 100,000 to 1,000,000 cycles. Furthermore, the electrons tend to leak out over long time periods of many years, causing flash to lose data, which makes flash-based memory systems unsuitable for long-term backups. In this diagram, you can see how a solid-state drive using flash memory works. Blank flash memory stores the value 11111111. So we have all ones here. If I want to write the value 10010100, I have to pop electrons into the second, third, 5th, 7th, and 8th flash locations, those bit locations. I'm pretending we only have a byte here. If later I wish to change that stored value to 10100011, I must first erase that block of flash memory before I can program the new data value. Generally, I must erase flash memory in the size of an erase block, and this is typically 4 kilobytes. Waiting for this block erasure procedure causes something called write amplification, where successive writes to an SSD become progressively slower. To avoid this problem, typically erase the SSD ahead of time whenever space has been freed on it. And there's an ATA command called trim that facilitates this process. One other issue that has to be dealt with SSDs is the fact that each cell can only be written to and read from, or generally written to, erased and written to, a fixed number of times. This is typically between 100,000 and 1,000,000. So to spread out the writes across the entire SSD, the SSD moves data around the drive as files are updated, and it also reserves a certain amount of free space unused so that that free space can be swapped in and out with space that's in use later. This process, called wear leveling, has the advantage of dramatically increasing the useful life of the SSD and reducing write amplification whenever clean blocks are made available. However, in order for the write amplification reduction to be effective, the operating system and the underlying file system must support the ATA trim command. And furthermore, it's impossible to ensure that the disk is secure against forensic data recovery because it may not be possible to overwrite and properly erase the reserved cells of memory that have been taken out of service. Thus, a used solid-state drive should be physically destroyed instead of attempting to resell it, which can be an issue because a solid-state drive has a higher upfront cost. So in summary, disks are attached to the system via some kind of bus. The newer bus styles are SATA and SAS. These modern disks are addressed using logical block addressing. They're partitioned either with DOS partition tables or GUID partition tables. GPT use will increase as the size of disks becomes larger owing to the limits of the DOS partition table. And solid-state drives offer higher performance at a higher initial cost, subject to the requirement of wear leveling, and subject to not being able to be safely resold due to the inability to forensically secure the data on the drive. In this lecture, I'll be discussing disk scheduling. I'll be introducing the purpose of disk scheduling, talking about some classical and historical disk scheduling algorithms, talking about native command queuing and disk schedulers that are currently in use in the Linux kernel, and then I'll talk a little bit about how I/O requests can be efficiently scheduled on solid-state drives. The scheduling serves two purposes. Disk scheduling serves two purposes. The first of these is to arbitrate disk access among different programs. This ensures that competing programs have access to disk resources, and that a single program cannot monopolize the disk resources in such a way as to prevent other programs from accessing the disk. With mechanical hard drives, scheduling algorithms historically have also attempted to improve disk performance by reducing the number of seeks required, reducing the number of times the drive head needs to be moved. If the drive head has to be moved too many times, a lot of throughput can be lost from the disk because we're waiting on all those seek times to occur. The simplest scheduling algorithm would be the first come, first serve algorithm, which is implemented in Linux as the no-op scheduler. This algorithm is extremely straightforward. It simply consists of a FIFO queue into which new requests are added. The requests are removed from the queue in order, one by one, and these requests are sent to the disk for processing. Now, there's no reordering of the queue. This is a first come, first serve ordering. So back-to-back requests for different parts of the disk may cause the drive head to move back and forth across the platters, wasting quite a bit of time with seeks. Historically, several attempts have been made to try to improve this behavior. One example would be the scan algorithm or the elevator algorithm. And in this algorithm, the drive head only moves in one direction. It serves all the requests in that direction before moving back in the other direction. This is called the elevator algorithm because it's modeled after how an elevator works in a building. The elevator leaves the ground floor, moves to the highest floor, stopping along the way to add passengers traveling up, remove passengers at whichever floor they wish to stop on, and then once the elevator reaches the highest floor, turns around and comes back down. Same process here. In this example with the scan algorithm, assuming that the head starts at sector 1, and this request for sector 50 comes in while sector 61 is being processed, the algorithm is going to process the requests in order 3, 12, 32, 40, 42, 61, 84, 97. And since that request for sector 50 came in while 61 was being processed, that request for sector 50 is going to have to wait until the head changes direction and returns to sector 50. Now, there are a few optimizations of the simple scan algorithm. The original algorithm proposed that the head would move all the way from the beginning of the disk to the end of the disk and then all the way back to the beginning. The look algorithm improves upon this behavior by moving the head only as far as the highest number request before changing directions and moving it back down. The circular versions of the algorithm, cscan and clook, only serve requests moving in one direction. So for example, with circular scan, the head would start at the first sector, move all the way to the end of the disk, servicing requests, and then come all the way back down to the first sector without servicing any requests and start the process over again. These are historical algorithms in the sense that with modern drives, we have LBA or logical block addressing, and so we don't actually know where the disk is placing data physically. This type of algorithm was used historically with cylinder head sector addressing, where we knew the physical properties of the disk, and the idea here was to reduce average seek time. At no time did we know where the platter was. That was up to the disk to figure out. So there was no way to reduce rotational delay, only minimize seek time. Another algorithm that attempts to minimize seek time is the shortest seek time first algorithm, or SSTF. This algorithm actually orders requests by sector location. So when the request for sector 50 comes in, it's kept in an ordered queue, a priority queue, and the next request to be served by the disk, these requests are still sent out one at a time, is chosen by looking at whatever request is closest to the current disk position. Historically, this could result in starvation, because if a bunch of requests come in for one piece of the disk, requests for the remainder of the disk might not be processed for lengthy periods of time. Furthermore, once again, with logical block addressing, the operating system doesn't really know where the sectors are laid out on disk, and so this algorithm doesn't really work with modern hard drives. Also, with solid-state drives, this algorithm assumes there's a disk head, which, in the case of a non-mechanical drive, there is not. In the Linux kernel, an approximation to shortest seek time first was implemented with the Anticipatory Scheduler. This was the default scheduler from 2.6.0 through 2.6.17. It was removed to 2.6.33 because it's obsolete. The idea behind the Anticipatory Scheduler was to approximate shortest seek time first by ordering only the read requests into an ordered queue, into a priority queue. If the next read request was close to the current head position, that request would be dispatched immediately. Otherwise, the scheduler would actually wait a few milliseconds to see if another request arrives for a nearby location. And starvation was avoided in this algorithm by placing expiration times on each request and adding preemption, so that if a request was waiting too long, it would go ahead and be serviced regardless of its location. The idea here was to reduce overall seeking. There was a separate queue for write requests because write requests could be performed asynchronously. We did not have to wait on those requests to be completed before a process could continue doing useful work. This algorithm was shown with low performance drives to improve performance on web server applications. However, it was shown to have poor performance for database loads, where there were a lot of random reads and writes on the disk. And with high performance disks, this algorithm actually breaks down. Modern hard disks generally do qualify as high performance disks. The reason being is that they implement something called native command queuing. This is a feature of newer SATA drives, and basically native command queuing leaves scheduling of disk requests up to the disk itself. The disk circuitry and firmware makes the decision about which request to handle next. To do this, the disk has a built-in priority queue of about 32 entries, and the disk is able to schedule its requests automatically, taking into account both the seek time and the rotational delay, since the disk knows the location of the platter. This makes modern disks much more efficient, and this works with logical block addressing. The operating system's role with this type of hard disk is really more arbitration of the disk resources among the different programs running on the system. One modern Linux scheduler that can be used for such arbitration is called the deadline scheduler. And in this scheduler, the kernel maintains separate request queues for both read requests and write requests, similar to the anticipatory scheduler. Reads are prioritized over writes because processes typically block or stop and wait while waiting to read something from the disk. Thus, writes can be done later at some point when it's convenient for the operating system. The waiting time in each queue with the deadline scheduler is used to determine which request will be scheduled next. A 500 millisecond request time is the goal for read request. This is the time it would take to start the request, with a 5-second goal to start a write request. This scheduler may improve system responsiveness during periods of heavy disk I/O at the expense of data throughput, since each request has a deadline, and the longer a request has been waiting, the sooner it will be scheduled. This is especially useful for database workloads because there are many requests for different parts of the disk. However, for web servers and other services that try to access large quantities of data located in the same location on the disk, this particular scheduler can actually reduce total throughput. Completely fair queuing is a somewhat different idea, where instead of actually scheduling the I/O requests, the completely fair queuing model schedules processes or running programs to have time slice access to each disk. And essentially, this CFQ scheduler gives each process an I/O time slice, and that process can do as much I/O on the disk as it would like within that time slice. When the time slice expires, the CFQ scheduler moves on to the next process and gives it access time to the disk. There is a little bit of similarity here to anticipatory scheduling, since a process can send another request during its time slice and try to get that request in without having a lot of seek time. However, this algorithm can waste time if a process does not immediately turn around and send another request. Thus, it can reduce the overall disk throughput, since there could be idle times while waiting to see if another request will come in before a time slice expires. This has been the default scheduler in Linux since 2.6.18. Now, for solid-state disks, we have to choose a scheduler that accounts for the fact that there's no seek time to worry about on the disk. The anticipatory scheduler, the elevator algorithms, shortest seek time first,
All of these algorithms can actually reduce performance on a solid-state drive because they make assumptions about minimizing head seek time, and we have no heads to move with a solid-state disk. Completely fair queuing can also reduce disk performance because of idling at the end of a time slice. That's true for any disk. So what do we do to maximize performance for a solid-state drive? There are really two good choices for a solid-state drive. There is the NOAA or FIFO scheduler. This works well for general-purpose systems. However, when there are heavy I/O workloads and we want to maintain system responsiveness, the deadline algorithm is useful, since other processes will have more opportunities to access the disk. In summary, operating systems are arbitrating disk access among different processes to prevent one process from monopolizing the disk, preventing other processes from having access. On older disks with cylinder head sector addressing, the operating system was also attempting to reduce seek time, thus improving aggregate disk performance. However, newer SATA disks with native command queuing schedule themselves to reduce both seek time and rotational delay. Thus, algorithms that attempt to minimize seek time are unnecessary. Furthermore, with solid-state drives, scheduling mechanisms that are based on old mechanical assumptions can actually reduce performance. So for SSDs, we're really only interested in arbitration. In this lecture, I'm going to discuss file systems. I'll be providing an overview of the purpose of file systems, discussing metadata that they store, explaining how we create a file system through a process known as formatting, talk about some issues with file systems, including fragmentation and journaling, briefly discuss some internal layouts used by different file systems, and finally, talk about mounting and unmounting file systems to make them available to users. A file system is responsible for laying out data on a persistent storage device and ensuring that data can be retrieved reliably. File system is an abstraction of disk space. It provides routines for querying, opening, and closing files, and providing human-readable names for files, and some kind of organizational structure for files, typically through directories or folders. Without a file system, we would have to access disk by physical location, by address, and each program would have to reserve certain address limits for its exclusive use. File systems, in addition to performing this abstraction, also arbitrate disk space among different programs and different users of a computer system. File permissions allow users to have a certain degree of privacy, while file quotas ensure that one user does not monopolize the entire system by utilizing all disk space. File systems are also responsible for storing metadata or information about each file. This includes the file name, file size, who owns the file, what group that owner belongs to, what permissions exist for each different category of users on the system to access that file, as well as to provide certain timestamps. On Unix, we have the inode creation time, file modification time, and optionally the last file access time. Metadata records also include internal information that is important for the file system itself, such as pointers to the actual data on disk, and a reference count for how many different names refer to the same file, a system called hard links. We create a file system by taking an empty partition, or a partition that we're ready to reuse, and formatting it. Formatting, quite simply, is the process of making a new file system on an existing partition. Formatting typically destroys the structure of any file system that was previously installed on the partition. Thus, when you format a partition, you lose the access to its contents, at least through standard tools. However, unless that free space, unless that partition is securely erased, the contents that were formerly on the partition can still be recovered using forensic tools. The only safe way to switch between file systems on a single partition is to back the data that's on that partition up to another disk, format the partition using whatever the new file system would be, and then restoring the data from the backup. There is no safe way to change a file system type in place without losing data. File systems do suffer from a few issues. Over time, sections of a file in a file system can become non-contiguous. In other words, a file gets split over different parts of the disk. And in the process, that also splits up the free space, so that when new files need to be allocated, they have to be split up to take advantage of smaller blocks of free space. This is a situation called fragmentation. It's worse in some file systems than others. Fragmented file systems were a big problem with mechanical hard drives, simply because a fragmented file requires a seek to move from the location of the first fragment to the location of the next fragment, and possibly further seeks if there are more fragments. Not so much a problem on solid-state drives, however, since there's no seek time. And file systems can get around this problem either with offline defragmentation tools that the system administrator can run manually, or they can use fragmentation avoidance strategies or automatic on-the-fly defragmentation. Another issue that can occur with file systems is that a single high-level file system operation typically requires several low-level steps in order to complete. If the computer should crash or power be lost in the middle of those steps being performed, the file system could be left in an inconsistent state. A solution to this problem is called journaling, and the way this works is by recording all the steps that are to be taken in something called a journal, a special part of disk space reserved for this particular information. Records all the steps that are going to be taken prior to taking the steps. Thus, if the system should crash in the middle of a file system high-level operation, all that needs to occur is the journal simply needs to be replayed next time the file system is mounted, and the steps can be carried out again and leave the file system in a consistent state. Internally, file systems may use one of several different approaches for storing data on the disk. Simple layouts called the file allocation table, which simply has a single table on each partition to store metadata and the addresses of data segments for each file. File allocation table type storage methods are limited only in terms of how big the file allocation table can be. And these limitations specify, among other things, the maximum size a file can be and how many files can be on the system. Another approach is to use something called inodes, which are data structures on Unix systems that contain the metadata for a file, including pointers to the actual data. Inodes do not store the file names, however. These are stored in a separate structure called a directory that maps file names to inodes. The maximum number of files that a single file system can hold is limited by the number of inodes created when the file system is formatted. This can be a particular problem for file systems that wind up storing a really large number of very small files. There could be plenty of space left on the file system, on the partition. However, if the number of inodes is exhausted, then no more files will be able to be created. Another approach to storing files and laying out data on the file system is through the use of extents. Extents support larger maximum file sizes because they're designed to allow files to be composed of several non-contiguous blocks of space, much like fragmenting that could occur with a file system that doesn't use extents. Extent information is stored with the metadata in the file inode or some other type of data structure for file systems that support extents. Now, regardless of how the file system lays out its data internally, we need to make the file system available to users and programs on the computer. To do this, we perform a process called mounting. Mounting is the act of making a file system available to the users of the system. Opposite process is called unmounting, which is disconnecting a previously mounted file system. Unix systems mount file systems at mount points, which are simply directories somewhere within the overall directory structure of the system. So if I plug in a flash drive on a Linux machine, for example, that flash drive may be mounted at /media/my_drive. I can mount a large number of different file systems this way at the same time. And I can make all of the different file systems appear to be part of one directory structure. On the other hand, Windows systems use drive letters, where the letter C is reserved for the system partition, the one on which Windows is installed, and A and B are reserved for floppy drives. Windows supports a maximum of 26 file systems to be mounted at once, simply because that's the number of letters that are available to assign to drives, to assign to partitions. So in summary, file systems organize data, store metadata, provide an abstraction of the underlying storage medium, and arbitrate access to the storage space. We create file systems through a process known as formatting. We can make file systems more robust against data loss during a power failure through the use of journaling. Internally, file systems use various different mechanisms for laying data out on disk. No matter how they work internally, we can make them available to a running system by mounting them. In this lecture, I'm going to discuss features of the Central Processing Unit, or CPU, that are useful for supporting multiple applications sharing a computer system simultaneously. In particular, I'll introduce multiprogramming and discuss the hardware requirements to support multiprogramming. I'll discuss CPU privilege modes, x86 protection rings, mode switches, and briefly introduce interrupts. First concept to introduce is multiprogramming. And multiprogramming is simply the idea that we can run multiple processes or multiple instances of potentially several programs at the same time. And we can do this by having the CPU switch quickly among the different processes, enabling all of them to make forward progress per unit of human perceivable time. The CPU will switch quickly enough to provide the illusion that all the processes are running at the same time, even if we only have one processor core. The vast majority of modern computing systems, with the exception of some special purpose systems, are multiprogramming systems. Some of the old computer systems of the day were batch systems that only ran one application at a time. Now, in order to support multiprogramming, we have to have certain features of our computer hardware. First of these is an interrupt mechanism for enabling preemption of running processes whenever some kind of event occurs. We have to have a way of stopping a process, handling an event, and then restarting the process. We need to have a clock so that we know how long a process has been running, and we need to have CPU protection levels to restrict access to certain instructions to prevent processes from hijacking the system or just trying to bypass the operating system altogether. We also need to restrict access to memory in order to prevent reading and writing to memory that the particular process does not own, belongs to somebody else. 2 CPU protection levels are sufficient: a protected mode and a privileged mode. These modes are also called the supervisor mode or kernel mode and user mode. In kernel mode, all instructions on the CPU are enabled, and the kernel can access all memory on the system. In user mode, the CPU disables all the privileged instructions and restricts most direct memory operations. Thus, a user program must make a system call to the operating system to request memory or perform other resource allocation tasks. In this way, the user processes are effectively sandboxed both from the system and from each other. On Intel-based systems, x86 and x86-64 systems, there are actually 4 modes available. These are implemented by what are known as x86 protection rings, which consists of 4 privilege levels numbered 0 through 3. Ring 0 has the greatest number of privileges. Code executing in ring 0 can execute any instruction the CPU provides and can access all memory. Ring 3 has the fewest privileges. All the instructions are restricted to the set of instructions that are relatively safe. In practice, most operating systems actually only use ring 0 and 3. OS2 and Zen are the notable exceptions that make use of ring 1. Newer systems with virtualization extensions, either the Intel VTX extensions or the AMD extensions, add an extra privilege level below ring 0. This is colloquially sometimes referred to as ring -1. And this mode enables instructions that allow multiple operating systems to share the same processor. These instructions help systems support hosting multiple virtual machines at the same time. Now, regardless of the number of modes available, whenever we wish to change modes for whatever reason, we have to perform something called a mode switch. And that occurs whenever the CPU switches into user mode, kernel mode, or hypervisor mode, or whenever an x86 CPU changes which protection ring is presently effective. Mode switches have the potential to be slow operations compared to other machine instructions, depending upon the hardware. A notable example was the first generation of Intel Core 2 series processors, in which the mode switches into and out of hypervisor mode were quite slow. One situation in which a mode switch might occur is when something called an interrupt happens. And an interrupt is simply a situation in which the currently executing code is interrupted so that an event can be handled by the operating system. Interrupts can fall into two categories. You can have involuntary interrupts, which are external to running processes. These consist of things such as I/O interrupts, which are generated every time you press a key on the keyboard or perform any other I/O task. Clock interrupts, which are timer mechanisms that can be scheduled to go off at a particular time. And page faults, which have to do with the virtual memory subsystem. Interrupts can also be voluntary, in other words, created by a process that's running. System calls and exceptions, such as setFault or divide by zero actions, can result in interrupts as well. And the CPU provides hardware mechanisms for detecting when an interrupt is occurring and handling the interrupt. So in summary, multi-programming systems allow multiple applications to run simultaneously. Implementing multi-programming requires support from the hardware. In particular, we need CPU privileges, we need a clock, and we need some kind of interrupt handling mechanism. The CPUs used in multi-programming systems need to have at least 2 privilege modes. Intel x86 systems support 4 or 5 modes depending on the processor. Mode switches can be expensive in terms of performance, so we don't want to do them more than necessary. And interrupts enable hardware events to be delivered to applications, and they allow applications to yield control of the system while waiting for events or waiting for services. Lecture, I'm going to discuss kernel architectures. I'll begin by introducing the functions of the kernel, explain the separation between mechanism and policy, talk about some seminal early kernels in the history of computing, and then introduce the differences between monolithic kernels and microkernels. A kernel provides 2 functions, the same 2 functions as in the operating system. It provides abstraction and arbitration. The kernel provides abstraction in the sense that it provides a mechanism for programs to access hardware, a way to schedule multiple programs on the system, and it provides some method for inter-process communication, or IPC, a way for programs to send messages to each other or send messages to hardware devices or out to the network. Kernels also provide abstraction mechanisms. They ensure that a single process or running program can't take over the entire system. They enforce any kind of security requirements, such as access privileges that might be in place on the system. and they minimize the risk of a total system crash from a buggy application or device driver. It's important to distinguish between mechanism and policy when discussing the internal components of an operating system. Mechanism, put simply, is the software methods that enable operations to be carried out. An example of a mechanism would be code that, implemented inside a device driver, sends a message to a device that causes that device to blink a light, enable a camera, or perform some other hardware level operation. Policy, on the other hand, is a set of software methods that enforce permissions, access rules, or other limits against applications. So a policy, for example, would be something that said that only users who met certain criteria could send a message out to a hardware device to blink a light or enable a camera or perform some other hardware function. It's a generally accepted principle of good design that mechanism and policy should be separated as much as possible. An early kernel that separated mechanism and policy quite well was the Regenzentralen RC4000 monitor kernel. This kernel was developed in 1969 primarily by Per Brink Hansen for the Regenzentralen RC4000 computer system. This was a computer system that was developed in Denmark. And the central component of the system was a small nucleus, as Brink Hansen called it, called monitor, which allowed programs to send messages to each other and allowed programs to send and receive buffers, which were essentially types of messages for hardware, to and from different hardware devices. In particular, at that time, they had a card reader, a tape reader, and a printing style output device. Other kernels with different scheduling mechanisms and other capabilities could be run under monitor. In those days, it was not clear that multi-programming was really a desirable feature for computing. Thus, someone could write a multi-programming capable kernel and actually run that as a subkernel under the monitor system. Importantly, this was also the first system that allowed subkernels and systems-level software to be written in a high-level language, in this case, Pascal. The system performance was actually quite awful. Brink Hansen stated that the operating system itself was so slow at performing its IPC tasks that there were a number of issues with the system completing tasks on time. However, the system was stable and reliable, making it successful in computer science history, even if it was not a successful product commercially. On the other hand, the opposite extreme would be the Unix kernel. This was developed at Bell Labs by a team headed by Ken Thompson and Dennis Ritchie, also starting in the late 1960s. The difference between the Unix kernel and the RC4000 monitor was that the Unix kernel's design implemented performance. Thus, instead of having a very small kernel that simply provided an IPC mechanism and some basic resource collision avoidance, this kernel actually provided all the device drivers, all the scheduling, all the memory management, including support for multi-programming, directly inside the kernel. This kernel was an early example of what would later be called a monolithic kernel. A monolithic kernel is a kernel that contains the entire operating system in kernel space, runs all of the operating system code in privileged mode, or ring 0 on an x86 system, and divides the different functions of the operating system into subsystems of the kernel. All of these subsystems, however, are run in the same memory space. This has the advantage of higher performance, but the disadvantage is that the kernel becomes less modular and more difficult to maintain, and the components are not separated very well. So a crash in one component could in fact bring down the entire system. The opposite of this, the RC4000 style kernel, is what we now call a microkernel. And a microkernel basically contains the bare minimum of code that's necessary in order to implement basic addressing, interprocess communications, and scheduling. This basic amount of code runs in kernel space, Everything else runs in user space, often with lower privileges. As a general rule of thumb, microkernels contain less than 10,000 lines of code. Microkernel-based operating systems tend to be quite modular because they divide the operating system functions between the kernel and a set of servers run in user space. However, because many of the core functions of the operating system are performed by user space components, which have to communicate with each other via the kernel, performance does suffer. Thus, most kernels that are in use today are a hybrid of these two designs. I'm going to introduce Murphy's Law of Reality, sort of an extension of the Murphy's Laws with which you may be familiar. And my definition of Murphy's Law of Reality is simply that reality is the hazy space between the extremes of competing academic theories in which everything is wrong in some way, at least according to the theories. This idea of a hybrid kernel architecture is a controversial one. Some people do not like to use this terminology at all. Many people prefer to keep the binary classification of monolithic kernel and microkernel. However, if we look at modern kernels, typically the monolithic versions of modern kernels are broken into modules that can be loaded and unloaded at runtime. This helps to increase maintainability of the kernel. True microkernels today would have unacceptable performance. Thus, microkernel-based systems typically have some of the features of monolithic kernels, such as more device drivers and other code that runs inside the kernel's memory space. Some examples of different types of kernels. For monolithic kernels, in addition to the System 5 Unix kernel, which is a descendant from the original Unix kernel, we have the Linux kernel, BSD, MS-DOS, and Windows 9X kernels. Windows NT, XP, Vista, and 7, if you don't prefer to use the hybrid terminology, would also qualify as monolithic kernels. And the Mac OS X kernel falls into the same category. In terms of microkernels, the RC4000 monitor kernel would have been the earliest. However, there have been plenty of other examples, including Mach, L4, the MIT exokernel project, and the idea, at least, behind the Windows NT kernel, which was based upon a microkernel design. The same is true of the Mac OS X kernel, since that was originally based on the Mach microkernel. However, those have been heavily modified and now have many properties of monolithic kernels also. So in summary, the kernel is the minimum layer of software inside the operating system that provides the basic foundations for abstracting away details of the hardware and arbitrating between multiple applications. When the absolute bare minimum implementations are used, we call the result a microkernel. Monolithic kernels, on the other hand, have all their major OS components contained within them, running everything inside kernel space to improve performance. Two early influential kernels were the RC4000 monitor, an example of a microkernel, and the original Unix kernel, which was an example of a monolithic kernel. In practice, however, most modern operating system kernels are hybrids of the two designs and have features of both kernel types. System via the command line. In part 1 of this lecture, I'm going to discuss command line operation, introduce paths in the file system, discuss the file system hierarchy, talk about the contents of the root directory, give an overview of several top-level directories, briefly discuss configuration files, and introduce the concept of man pages. In Linux, the command line is the older type of interface, user interface to the system. It is a text mode interface that predates the development of graphical user interfaces, or GUIs. The command line uses the keyboard exclusively. In general, there is no use of the mouse. And it works by having you type in a command, followed by any arguments to that command, and then pressing enter. The command runs, and if there are any results to be displayed, the result of the command is displayed below where you enter the command. At all times, the command shell, or the program that processes the commands that you're entering, is in something called a working directory. That working directory is a location on the file system in which any file that you create by default will be placed, and you can open files by default without having to give any kind of path information for them. You can figure out what the current working directory is by using the pwd or print working directory command. You can change directories using the command cd. Running the command cd with no arguments will take you to your home directory. And you can list the contents of any directory with the ls command. It's typical that someone who's been using Linux for some time will compulsively issue the ls command every time the cd command is used, so that you can maintain some kind of awareness about how the file system is structured. Paths in the file system can be given in one of two ways. They can be given as an absolute path, meaning that they have a leading slash, such as /etc/nittab or /opt/condor/bin. Relative paths, on the other hand, are relative to whatever current working directory the shell is in. Thus, a relative path myfile.c is going to refer to a file named myfile.c located in the current working directory. The path tests/final/p_allops is going to refer to a file that is in the final subdirectory of a tests directory that can be found in the current working directory. There are also some special relative path name components that can be used. A single period, a single dot, references the current working directory. Two periods, or two dots, references the parent directory. Thus, path /foo/dot/bar means go up one directory from the current working directory, then go down into its subdirectory foo and access a file called bar. Notice that the single dot alone as part of a directory path generally has no effect, because it refers to the current directory. Now, all directories on a Unix system are organized according to the file system hierarchy, and there is a specification available for the file system hierarchy, which different distributions follow to different levels, and the standards get interpreted a bit between systems and distributions. In any case, however, the root directory of a file system is located at a path consisting of a single /. And you can change to the root directory by running cd and then as the argument to cd, just a single /. In this screenshot, we can see we're on a system. I've run cd/ and then run ls to look at the contents of the root directory. There are a number of top-level directories that are fairly standard inside the root directory on a normal Linux system. These include /bin, which is where the minimum set of programs needed to work with the system is located, /dev, which contains entries corresponding to hardware devices on the system, /etc, which contains the system-level configuration files, /opt, which contains optional software typically added by the system administrator, /usr, often pronounced /user, which contains software that ships with the Linux distribution, /var, which contains rapidly changing files such as log files, /lib, which contains system libraries used by other programs, /media, into which automatic mounting systems will mount removable drives and devices, /mnt, often read as /mount, which is where the system administrator can manually mount removable devices or network shares, /root, not to be confused with the root directory, media is actually the home directory for a super user or root user. /sbin contains super user binaries, or programs that are intended to be run only by the system administrator. And /temp is where temporary files are typically stored. As mentioned a moment ago, system-wide configuration files generally go in /etc. Two important examples of files in /etc include /etc/emit tab, which sets the default run level, or whether the system is going to boot to text mode or graphical mode, and /etc/fstab, which contains the file system table, indicating to the kernel where to find different file systems that need to be mounted at boot time. Configuration files in general on Linux can be edited with a text editor. On a pure command line system, this might be the VI text editor. VI is the one text editor that is generally expected to be present on any Unix system. If you need help on a command or some configuration file within the system, there is a built-in help facility called man pages or manual pages. Man pages allow you to get help on particular commands and other features of the system simply by typing man, a space, and then the command or feature on which you would like to get help. To navigate through a man page, you can use the up and down arrow keys and then use the Q key to exit the manual facility. In the next part of the lecture, I'll discuss file permissions and other basic issues related to running a Linux system. Sure. I will continue discussing the basics of utilizing a Linux system. In particular, I'll talk about file ownership, file permissions, listing running processes, finding libraries used by a program, determining the absolute path of a program, and discuss the role of the superuser on the system. First, we'll start with file ownership and permissions. Each file on a Linux system is going to have an owner, a group, and access permissions. This information can all be found by running the ls command with a -l argument. It is possible to change which user on the system is the owner of the file using the chown command, or change owner, CHOWN. The change group, CHGRP command, allows you to change which group a file will be associated with. And permissions for a file can be changed with the chmod, or CHMOD, for change mode command. Each file has 3 types of permissions for each of the 3 levels of access. Access controls are set with a bitwise OR of permission bits. A value of 1 is used for execute permissions, meaning that the file can be treated like a program and executed directly. A value of 2 is used for write permissions, meaning that someone could change or delete a file. And a value of 4 is read permission, being able to read the contents of a file. Individual file permissions are supported for 3 classes of user: the owner of the file, members of the group with which the file is associated, and so-called world permissions, or all users on the system. Changing file permissions can be done with the CHMOD command, and by example, a file can be set to be world readable and executable, but writable only by its owner using the command chmod space 755 space the name of the file. A file could be set to be write protected and readable only by the owner of the group by running the same chmod command, only with permissions 440. In the first example, 755 means permission 7, which is 4 plus 2 plus 1, meaning read plus write plus execute, for the owner, that's the first number of the 3. The first 5, the second number of the 3, sets permissions for the group, which is 4 read plus 1 execute makes 5, and the same for read plus 1 execute for the world, which is the third number. In the 440 case, the 4 means read only for the owner, the second 4 means read only for the group, and 0 means no access whatsoever by people who are not members of the group with which the file is associated. Permissions on a directory work slightly differently. If a directory has execute permissions, The contents of the directory can be traversed, allowing access to readable files and subdirectories within the directory itself. Read permissions on a directory are necessary in order for a directory to be listed. And for someone to obtain a directory listing with ls, they must have both read permissions and execute permissions for that directory. Files can be deleted on a Linux system with the rm command. Rm is short for remove. Entire directories can be deleted using rm-rf and then supplying the directory name to delete. This can be an extremely dangerous command if run incorrectly. For example, running rm-rf/ as the root user will delete every single file on the system, and it will not ask first. This will leave the system in a destroyed state. There is also no undelete function on most Unix file systems. Once the rm command has been used, the file is simply gone. And unless that file has been backed up, it is not easily recoverable. When working with a Linux system, it's often useful to see what programs or what processes are running on the system. There are two commands that can be utilized in order to find this information. The first of these is the ps command, which stands for processes. ps space ax will allow you to see all processes currently running on the system. To find out which user owns each process, run ps space aux. The top command is a useful command for getting current information about the state of the system, including running processes, amount of available memory, and amount of CPU that's being utilized. This command displays the processes that are using the most CPU time and updates itself every second or two. This command can be exited by hitting the Q key. To see what dynamic libraries are used by a binary program, not a script, but an actual compiled binary application, one can use the LDD command. So if one were to run the LDD command on, for example, /user/bin/events for systems that have the GNOME PDF reader installed, one would find out which dynamic libraries were needed in order for that application to run. It's also possible to find out the absolute path name of an installed program to see where it actually resides on the file system. This is done with the which command. For example, typing which events should display /user/bin/events on most Linux distributions, provided of course that software is installed. Finally, there is one administrative user on the Linux system called the super user that has the account name root and has privileges to read, write, or delete any file, change system settings and install software,
Good morning, Tita Marie, Ate
and
Jessie.
perform other administrative tasks that are
Salamat.
normally forbidden of ordinary users. On some
Salamat
Linux
sa
distributions
paayuda.
such as Ubuntu and on Mac OS X, the root user is disabled by default. However, many other distributions,
Good
including Red Hat
morning, Tita
Enterprise
Marie,
Linux,
Ate
CentOS, and
Jessie.
Arch Linux, leave the
Salamat.
root user account enabled. On systems where the root
Salamat
user
sa
account has
paayuda.
been disabled, or on systems where the administrator would like to disable the root account, the sudo command allows authorized regular users to run a command as the super user. So for example, you could find the listing of the root's home directory by typing sudo ls/root. To switch to the super user temporarily on one of these systems, sudo su- and entering the user's password would allow the user temporarily to become the root user, even if the root account is disabled. On systems where the root account is enabled, su- has the same effect, except that the root's password must be entered instead of the user's password. Discuss interrupts and device input-output. When hardware devices on a computer produce events, they need some way of being able to handle those events within the operating system and deliver them to applications. And hardware devices are going to produce events at times and in patterns that we don't know about in advance. For example, we don't know which keys the user is going to press on the keyboard until the user actually presses those keys. If a cat walks across the keyboard, we're going to see a completely different pattern of key presses from which we would expect to see with a human user. Similarly, if we have incoming network packets for running a server application or even just a workstation, and we have messages coming in from the network, we don't know the order and timing of those messages. We also don't know when the mouse is going to be moved, or when any other of a whole bunch of hardware events is going to occur. So how can we get the information generated by these events and make it available to our applications for use? Well, we have two options. First option is to hold each device. Ask each device to continue information and retrieve that information. Or you can let the devices send a signal over the application and have the operating system stop whatever it's doing and prevent everything. This is called an interrupt. The polling model of input involves the OS periodically holding each device's information. So every so often, the CPU is going to send a message to each hardware device in the system and say, hey, you have other times the device will send back some data. It's a really simple design, extremely simple to implement, but there are a number of problems with it. What the operating system will do is it will preempt any running process. In other words, it will switch what we call context away from that running process to handle the event. Basically, it will move the program counter of the CPU to the code to handle that particular interrupt. This allows for a more responsive system than we could ever achieve through polling without having to waste a whole bunch of time asking idle devices for data. However, this does require a more complex implementation, and that implementation complexity begins at the hardware level. Specifically, within the CPU, we need to have a mechanism for checking and responding to interrupts. And this mechanism is implemented as part of the CPU's fetch execute cycle. In the process of fetch execute, the CPU is going to fetch an instruction from memory, increment the program counter, execute that instruction. But instead of simply going back to the next fetch, the CPU actually has to have additional hardware to check to see if an interrupt event is pending. If there is an interrupt pending, then the CPU has to be switched to kernel mode if it's running in user mode, so the privilege level needs to be escalated. Save the program counter by pushing it onto the stack, and load a program counter from a fixed memory location, and that fixed memory location is called the interrupt vector table, or IVT. So we load the program counter from the IVT, and then the CPU goes and executes that new instruction the next time the fetch execute cycle resumes. So the CPU actually moves from executing program code to executing code from the interrupt handler for a particular event. If no interrupt is pending at the end of an execute, then we simply go back to the next instruction, fetch. The interrupt vector table consists of an array of addresses of handlers. Each element in this array essentially gives the program counter location for the handler for a particular interrupt. This handler is going to be in a subsystem of the kernel for a monolithic kernel, or this handler might invoke a call to an external server or a microkernel. In any case, however, the first handler by convention, element 0 of the array, is always the handler for the clock. Then, handlers for different devices are in the array after the clock handler. So the interrupt vector is always mapped into the user part of memory. It's always available at all times so that the kernel can go and look up interrupt information whenever is necessary. An interrupt is processed by branching the program counter to the interrupt handler, executing the interrupt handling code, and then at the end of the interrupt handling code, there'll be an instruction to return from the interrupt. In the Intel assembly language, this is the IRET instruction, which loads the process program counter back from memory and pops the stack to get the original program counter back, and goes ahead and changes the CPU back to user mode. So it removes the privilege escalation. The interrupt handling mechanism is thus able to handle events from hardware devices without having to poll each device individually. I'll be discussing interrupt controllers. In particular, I'll introduce the old and new mechanisms for delivering interrupts from hardware devices to the CPU. These methods include the original programmable interrupt controllers and the new advanced programmable interrupt controller with message signals interrupts. Interrupt controllers provide an interface for hardware to signal the CPU whenever a device needs attention. It's important to note that this signal only includes a message that essentially says, hey, I'm a device, I need attention. The CPU historically then actually does have to go and poll the device to get any data that the device may have. The older mechanism performing this operation is called a programmable interrupt controller, or PIC, and it actually required dedicated lines to be added to the motherboard. The ISA, or Industry Standard Architecture bus, which dates back all the way to the first PC back in 1987, and older versions of the PCI, or Peripheral Component Interconnect bus, utilized this mechanism. The new mechanism, or the Advanced Programmable Interrupt Controller, is used on PCI Express devices and some newer PCI devices. Now, the old controller, or the Programmable Interrupt Controller, actually consisted of two Programmable Interrupt Controller chips that were attached to each other, with one of the chips being attached to the CPU. The so-called master chip was the one attached to the CPU, and pin 2 of that master chip was attached to a slave chip. Each pin on each of the two chips allows for 16 interrupt numbers to be created. Interrupts 0 through 7 correspond to the pins of the master chip, and interrupts 8 through 15 correspond to the pins of the slave chip. Now, it should be noted that since pin 2 of the master chip handles the slave chip, that the master programmable interrupt controller only supports an effective 7 interrupts. So there are only 15 usable interrupt hardware lines for devices. And these are numbered 0 through 15, but we have to skip the number 2. Now, historically, pin number 0, which corresponds in software terms to what we call interrupt request line, or IRQ0, was connected to the timer. Interrupt request line 1 was connected to the keyboard. Different ISA and PCI devices could then use the remainder of the master chip by connecting to IRQ lines 3 through 7. On the slave chip, pin 0, which corresponds to IRQ 8, was connected to the real-time clock. Pin 4, corresponding to IRQ 12, was connected to PS2 mouse. Pin 5, or IRQ 13, connected to the math coprocessor, which was a separate component from the main CPU in earlier PCs. And then pins 6 and 7, corresponding to IRQ lines 14 and 15, connected to the IDE controllers. These were used for disk and eventually for optical devices. This left pins 1 through 3 on the slave controller, or IRQs 9 through 11, available for hardware devices. Now, these interrupt lines on the motherboard were actually circuit traces. These were conductive paths etched into the motherboard that allowed interrupts to be received from devices. There were 15 lines available of the 16 that could be used by devices, with lines 0 and 1 reserved for the timer and PS2 keyboard, respectively. Actually, even before the PS2 reservation, the original AT keyboard. ISA and PCI add-in devices actually had to share interrupt request lines, and this sharing could lead to hardware conflicts that could lock up the system. It was thus up to the system owner to manage the sharing by setting little jumpers on the add-in cards so that the cards were using different IRQ lines. There were also performance issues when IRQ lines were shared, because the operating system actually had to poll each device sharing an IRQ to determine which device it was that raised the interrupt. Polling was still necessary in order to receive any kind of data from the device, regardless of whether it was sharing an interrupt line or not. On modern systems, a completely different interrupt mechanism is used, and this mechanism has a set of memory registers on what's called an advanced programmable interrupt control. And this set of memory registers is connected to a single shared bus each device on the system can use to raise an interrupt message by writing that message into one of the memory registers. These are called message signaled interrupts using the MSI and MSIX specifications. Essentially, each device, here I have a timer, RTC, USB host controller.
May echo. Hindi ko alam. Hoy, friendship, salamat. Salamat sa pang-MP natin dyan. Saan kaya yung nag-echo na yun? Hoy, friendship, salamat. Salamat sa pang-MP natin dyan. Kaya yung nag-echo na yun. Number of motherboards still have interrupt lines, physical interrupt lines. They have physical so that they can support legacy devices. A number of special legacy devices support message signal interrupts do solve a number of problems with interrupt request sharing. The original specification allows each device to use any one of 32 IRQ lines. The MSIX specification will allow each device to use up to 2048 virtual lines, virtual request options. This allows for less dependency and reduces the need to share interrupt request numbers by device, thus reduces the downtime necessary to see any from each device configuration. So, the main thing to take away from this is that the interrupt controller interrupt request mechanism only allows the device to raise a signal that says it's the CPU process at the device and if the information out of that device is interrupt handling at the hardware level, then move on to provided by the CPU, finally using the operating system. At the hardware level, devices are connected either via traces on the motherboard or via a shared messaging bus to the advanced programmable interrupt controller. CPU checks for hardware interrupt signals from this controller after each user mode instruction is processed. So after each instruction is executed, running some particular program in the system, the CPU actually checks to see if there are any interrupts that need to be processed. If the interrupt signal is present, then the kernel routine is called by the CPU in order to handle this interrupt. The interrupt dispatch routine is not implemented directly in hardware. It is actually a compact,
Fast routine that could be implemented in the kernel, often coded in assembly language. It has to be that fast. The specific interrupt handler is always a kernel routine, or in the case of a microkernel, an external server routine. And this specific handler depends upon the type of interrupt received. These are typically coded in C. So once again, fetch execute cycle, we check for an interrupt pending after each instruction is executed. If there is an interrupt pending, we escalate privilege to kernel mode, push the program counter onto the stack, in other words, save it so we can resume from that point in whatever programs are interrupting, and then go and handle the interrupt. We do this by loading the program counter, the new program counter, that is, from fixed memory locations provided to us by the interrupt vector table. The interrupt vector table gives us the address of all the different interrupt handlers. We need a separate handler for each type of interrupt. The clock requires different logic from the keyboard, for example. Other devices, such as, say, a webcam attached to your computer, needs different logic in order to process messages from it. So we have different interrupt handlers for each of these different devices. The table simply stores the addresses of each handler. And in our monolithic kernel case, the handlers are actually part of the kernel and mapped into kernel memory space. The interrupt vector table consists of a list of each of these addresses for kernel handlers, and conceptually is mapped into both kernel memory and user memory so that it can be accessed quickly. Historically, they started at address 0. However, the mappings are different depending on the architecture. On Intel-based systems, we have something called the interrupt descriptor table. And the IDT provides special instructions and data structures that are actually managed by the CPU itself so that interrupt handling can be as fast as possible and protection rings can be changed automatically. The IDT is simply a reserved block of RAM used by the CPU to jump quickly to a specific interrupt handler. This IDT is mapped into kernel space, which was originally beginning at address 0, but this mapping is actually flexible with modern CPUs and can be mapped to other parts of the memory space. The first 32 entries of the IDT are actually not used for interrupts per se, but they're actually used for CPU fault handlers. Then the interrupt vector table part of the data structure begins after the CPU fault handler table. When we actually go to handle interrupts, the handling occurs in the kernel, and this is done with two levels of interrupt handling: the fast interrupt handler and the slow interrupt handler. The fast interrupt handler is the piece of code that's invoked directly from the interrupt vector table whenever an interrupt occurs. This is the piece of code that the CPU is just going to jump to when an interrupt occurs. Fast handlers execute in real time, and they're called fast interrupt handlers because they need to be fast. The execution of one of these interrupt handlers needs to be short. If any large-scale data transfer needs to occur, say we need to get a lot of data from the device all at once, this operation is handled by having the fast interrupt handler and queue something called a task into the operating system's task queue. Whenever all the fast interrupt handlers for all the different interrupts are done executing, the CPU will go and check the task queue and execute any tasks that are present there. Part of interrupt handling that goes into the task queue is called the slow interrupt handling. And it's called this because it's not executed immediately, and it can be interrupted by other devices. So what happens if an interrupt request is received while we're still processing an interrupt from a previous request? Well, there's no problem if we're in the slow interrupt handler, because this processing is done in such a way that we can stop this processing and handle the new interrupt if necessary. What happens if we are still running a fast interrupt handler? Well, the new interrupt handler could be executed before the first interrupt handler is finished, and this could cause some major problems, especially if we get a new interrupt from a device that's sharing the same interrupt line as the one we're handling. So what we do is we make fast interrupt handling atomic. That is, we make it uninterruptible. On a single core system, this is as simple as disabling interrupts as long as we're running a fast interrupt handler. On multi-core systems, there are actual special machine instructions that facilitate atomic operations that are pegged to one CPU core. These atomic interrupt handling operations will run to completion without interruption by any other interrupt or any other request on the system. Thus, the longer an interrupt handler takes to run, the longer the system will be unresponsive to any interrupts. So what happens if a fast interrupt handler is coded in such a way that it takes too long? Other devices might be requesting attention at the same time that this long-running interrupt handler is executing. Worse, the same device that generated the original interrupt might now have more data to deliver to the OS before all the previous data is completely received. This could cause hardware failures, buffer overflows, dropped data, dropped messages, all kinds of issues at the hardware level. However, inside the operating system, this could lead to something called an interrupt storm, which is really bad. An interrupt storm occurs whenever another interrupt is always waiting to be processed whenever a fast interrupt handler finishes its execution. That could occur either because the fast interrupt handler is too long and needs to be split into a fast and a slow handler. This can also occur if hardware has certain bugs that cause it to raise spurious interrupts. If the operating system is perpetually handling interrupts, it never runs any application code. Thus, it never appears to respond to any user inputs. The result of this situation is
This is a browser game. You just go to a link to start playing the game immediately.
Interrupts. However, it's not doing any useful work. Thus, to the user, the system appears to be frozen. And when an interrupt storm occurs and this live lock situation results, the typical way out of this problem involves judicious use of power bank. So, interrupt handling is an important concept in order to support multi-programming systems. And interrupt handling, when these interrupt messages come through from hardware, is divided into two types of handler so that we don't get the interrupt storm. The fast interrupt handler executes atomically without being interrupted by anything else, but it must be fast. We enter that interrupt handler, do some very short operations, and immediately exit that handler. If any long-running operations need to occur as a result of the device interrupt request, we need to handle those operations inside the slow resources, and how the system and its processes view random access memory.
If you are looking to consistently generate high quality
In order to
for
run
your
any
business,
process
so that you
or
can
instance
sell
of
more
a
and create
program
more
on a
profit,
computer
here are
system,
3 things to
we
look
need to
for.
provide two
Number
critical
1, create
resources:
an online sales
access to the
not a
CPU
website. A
and
website
access
is
to
confusing
random
with all
access
the about
memory,
us.
or RAM, for storing and manipulating data. RAM is a type of dedicated hardware memory that is attached to the motherboard. It is separate from persistent storage or hard disk space. RAM is also volatile, which means that it loses its contents whenever power is interrupted to the RAM modules, including whenever the computer is turned off. At a low level, computer hardware presents memory to the operating system as one large block of space. This space is divided into bytes, and each byte in memory has a unique address that can be used to access it. A 32-bit architecture provides enough of these byte addresses to utilize up to 4 gigabytes of RAM. Above that amount, there is not enough space in a 32-bit number to store the address of any memory locations in excess of 4 gigabytes. Thus, a 64-bit architecture is required for systems with more than 4 gigabytes of architecture provides enough of these byte addresses. Each process or running instance of a program on a system uses a different view of memory. Process memory is divided into several pieces: the stack, the heap, global variables, and the text segment. The stack is used to store automatic variables or variables that are local to functions in the C programming process. Space on the heap is manually allocated and deallocated by the programmer when writing C code using the functions malloc and free. Free space for extra data is located between the stack and the heap, and the stack and the heap grow toward one another. Global variables are provided with their own section of memory, which is allocated between the heap and text segment. The text segment is used to store program code. This segment of memory is read-only and cannot be changed. As I mentioned in the previous slide, automatic variables are placed onto the stack. This placement is performed by the compiler when the program is built. Placement of data onto the heap is historically performed by the programmer, although many of these operations are now automated in modern dynamic languages. In the C and C++ languages, the programmer must explicitly request and release, or allocate and deallocate, heap space. In C, these operations are performed using the malloc and free functions, while the new and delete operators are used in C++. In Java, the programmer must explicitly allocate space on the heap using the new keyword. However, the Java runtime automatically determines which heap allocations are no longer in use and frees those locations automatically. This process is called garbage collection. Python provides both automatic allocation and garbage collection. Whenever a data structure requires heap space, the Python interpreter allocates it automatically. Once a data structure is no longer used by the program, the garbage collector deallocates it without program intervention. This process is called garbage collection. Use of heap memory and processes presents a challenge to the operating system because these allocations and deallocations are not known in advance. The compiler is able to track and report the amount of stack space needed, since the number of local variables in a function never changes in a language like C. However, the number of heap allocations may vary from program execution to program execution, making it impossible to know exactly how much space should be allocated in advance. Worse, heap memory allocations tend to be small and frequent, so the process of allocating memory from this section needs to be fast. This speed and dynamic availability needs to be maintained while the operating system shares the computer's RAM among multiple processes at the same time. In addition to sharing memory among processes, the kernel has memory requirements of its own. Aside from the kernel code and its own automatic variables, the kernel is filled with data structures that dynamically grow and shrink during the course of system operation. These data structures are numerous and include process control blocks, the ready list, scheduling queues, device access tables, and many other types of structure. Unlike some processes, however, all memory allocation and deallocation in the kernel is performed by the kernel programmers. In the Linux kernel, programmers can use one of a number of functions, including kmalloc, kzalloc, vmalloc, kfree, and vfree. The first issue that must be solved by the kernel is sharing memory between itself and a user space process. This sharing is accomplished first by dividing the memory into two regions: kernel memory and user memory. The kernel keeps its data structures, program code, global variables, and automatic variables in kernel memory, isolating these items from the running process. Process memory is placed in a separate region from the kernel, but the kernel is always available in memory. This mapping is necessary to maintain performance whenever an interrupt occurs, the process makes a system call to the kernel, or the process experiences a fault that must be handled by the kernel. So how do we go about running multiple processes at the same time?
Well, the first way we can consider, which is used in some types of embedded systems, is to divide the memory into fixed-size chunks called partitions. A memory partition is a single region of RAM that is provided to a single process. Both the program code and data associated with each process must fit within this pre-allocated space. If a process grows too large, it will run out of memory and crash. Furthermore, the maximum number of concurrent processes, called the degree of multiprogramming, is limited by the number of partitions available. Once all memory partitions are used, the system cannot start any new processes. This situation is exacerbated by the fact that small processes may not be using their entire partitions, resulting in wasted memory. In this lecture, I will introduce dynamic memory allocation at the system level. This method of memory allocation improves the degree of multiprogramming that a system can provide by allocating memory to processes as needed instead of ahead of time in fixed-size chunks. Fixed memory partitioning is fast and efficient in terms of overhead, but it wastes space and limits the number of concurrent processes to the number of partitions that will fit into RAM. Dynamic memory allocation resolves this issue by allocating memory to processes as it is needed. This mechanism increases the degree of multiprogramming that the kernel can support, but this improvement comes at a cost of greater complexity. In addition, there are trade-offs present in dynamic memory allocation that directly affect the performance of the system. These issues include efficiency, methods for tracking free space, algorithms for determining where to make the next allocation, and memory fragmentation. The primary issue with dynamic memory allocation is fragmentation. During execution, processes allocate free memory in chunks of varying sizes. Over time, regions of free space within memory become non-contiguous, with sections of allocated memory in between sections of available memory. This fragmentation could lead to serious performance issues, since program execution speed will drop dramatically if every data structure must be implemented as a linked list of small pieces. Furthermore, algorithms that try to perform on-the-fly memory defragmentation are extremely complex to implement and would also severely impact system performance. Since it is impractical to avoid or fix fragmentation, memory fragments are a significant concern when space is dynamically allocated. Small fragments of memory are useless to programs, particularly C and C++ programs, which require structures and objects to be allocated in contiguous memory regions. These structures are likely to be in various sizes that are not efficient to utilize for memory management purposes, so the systems will allocate a few more bytes than the structures actually require in order to improve efficiency of the memory tracking systems. Furthermore, structures and objects will be allocated and freed numerous times during program execution, further fragmenting the RAM. Over time, fragmentation can waste large portions of the system memory, limiting the degree of multiprogramming by making it impossible for new processes to start. There are two types of fragmentation, external and internal. External fragmentation occurs when free space in memory is broken into small pieces. Over time, as blocks of memory are allocated and deallocated, this type of fragmentation tends to become worse. External fragmentation is so bad with some allocation algorithms that for every n blocks of memory that are allocated to a process, the system wastes another half n blocks in fragments. With these algorithms, up to a third of system memory becomes unusable. The other type of fragmentation is called internal fragmentation. Internal fragmentation occurs because memory is normally allocated to processes in some fixed block size. Block size is normally a power of 2 in order to make the kernel memory tracking structures more efficient. Processes tend to request pieces of memory in sizes that do not fit neatly into these blocks. Thus, it is often the case that parts of a block are wasted as a result. For small memory requests, large portions of the block may be wasted. When a process requests heap memory, the kernel must find a chunk of free space large enough to accommodate the request. This chunk cannot be smaller than the requested size, since the process expects to use all the space it is requesting. Since the memory is divided into blocks for efficiency, the chunk of memory returned to the process is normally larger than the amount requested.
unless the process happens to request a whole number multiple of block size. I'm now going to introduce 4 classical algorithms for dynamic memory allocation: best fit, worst fit, first fit, and next fit. The first classic algorithm for dynamic memory allocation is the best fit algorithm. In this algorithm, the kernel searches for the smallest chunk of free space that is big enough to accommodate the memory request. Although best fit minimizes internal fragmentation by avoiding over-allocation, external fragmentation is a major problem. An attempt to reduce the external fragmentation in the best fit algorithm is observed in the somewhat counterintuitive worst fit algorithm. Using the worst fit algorithm, the kernel finds and allocates the largest available chunk of free space, provided it is large enough to accommodate the request. In theory, this allocation strategy leaves larger, and thus potentially more usable, chunks of free space available. In practice, however, this algorithm still fragments badly, both internally and externally. Aside from the fragmentation, both of these algorithms are impractical in actual kernel implementations because they must perform a search of the entire free list to find the smallest or largest chunk of memory. The need to search the free list is eliminated using the first fit or next fit algorithm. In the first fit algorithm, the kernel simply finds and allocates the first chunk of memory that is large enough to satisfy the request. This approach does result in internal fragmentation, and it also tends to create small fragments of free space that accumulate at the start of the free list, reducing performance over time. The next fit algorithm avoids the external fragment accumulation by starting the search for the next chunk of memory from the most recent allocation. In practice, only the first fit algorithm is used in the Linux kernel, and then only for embedded devices. This algorithm is called the SLOB allocator, which stands for Simple List of Blocks. For non-embedded systems that have the computational power for a more complex algorithm, slab allocation is used instead of any of these simple algorithms. Memory allocation. I will introduce the power of 2 methods with the buddy system and coalescence for allocating memory to processes. Then I will introduce slab allocation, which is used within the kernel to allocate kernel data structures efficiently. In the previous lecture, I introduced the classic algorithms for memory allocation: best fit, worst fit, first fit, and next fit. Now I want to introduce algorithms that are actually used within OS kernels to perform memory allocations efficiently. These algorithms are called power of 2 methods, and they work by maintaining information about allocated and free blocks in a binary tree instead of a list. At the top level, memory is divided into large blocks called superblocks. As processes request memory, these superblocks are divided into smaller subblocks from which the memory is allocated. Subblocks can be further divided, creating a hierarchy of block sizes. Algorithms based on this method are relatively fast and scale to multiple parallel CPU cores. These algorithms also reduce external fragmentation by coalescing free blocks, as I will discuss in a few moments. Some internal fragmentation does still occur, however. In this diagram, we can see 3 superblocks, 2 of which are partially in use. Each of the first 2 superblocks has been divided into 3 subblocks, and the third subblock of the first superblock has been further divided. When a process requests memory, the kernel must perform a search of the tree to find an appropriately sized block to handle the request. In performing this search, the kernel might subdivide an existing block into a smaller block to reduce the amount of internal fragmentation. Since this is a search process, a reasonably powerful CPU is required to make this operation efficient. Another improvement to memory management is to utilize a buddy system in the power of 2 strategy. In this allocation system, 2 limits are chosen to be powers of 2, the upper limit U and the lower limit L. The superblocks are the blocks of size U, and these blocks can be subdivided into blocks as small as L bytes. There are trade-offs in picking the size to use for L. Smaller size produces less internal fragmentation, since the block size more closely matches the smallest request sizes for processes. However, a smaller size for L means that there are more total blocks to be tracked,
which increases the size of the binary tree, using more RAM to store the tree and increasing the search time. On the other hand, a larger size for L reduces the search time and makes the tree smaller, but the amount of internal fragmentation increases. In addition to the block size limits, the buddy system also uses a technique called coalescence. Whenever a process frees a block, the kernel checks to see if either neighboring blocks is free also. If one or more neighbors, or buddy blocks, are free, the block is coalesced into a larger block, reducing external fragmentation. The coalescence algorithm is efficient since the maximum number of coalescence operations that must be performed is equal to the base 2 logarithm of u divided by L. By properties of logarithms, this value is equivalent to the base 2 log of u minus the base 2 log of L. Thus, for example, a system with a maximum block size u of 4096 bytes, or 2 to the 12, and a minimum block size of 512 bytes, or 2 to the 9, will require at most 3 coalescence operations to recreate the superblock. Returning a single 512-byte block whose neighboring 512-byte buddy is free will cause the two blocks to be coalesced into a single 1024-byte block. If the neighboring 1024-byte block is free, the two 1024-byte blocks will be coalesced into a 2048-byte block. Then, if a buddy 2048-byte block is free, the third coalescence will produce a 4096-byte superblock. The power of two methods are useful for allocating memory to processes where some internal fragmentation is acceptable. However, within the kernel, it is preferable to minimize both internal and external fragmentation to avoid wasting space. This conservative approach is needed since the kernel is always mapped to main memory. An efficient solution for allocating kernel memory is to use a slab allocation algorithm, in which kernel memory is arranged into fixed-size slabs. Each slab is divided into regions sized for specific types of kernel objects, including file descriptors, semaphores, process control structures, and other internal data structures. Initial layout of these slabs is performed at compile time. At runtime, several of each of the different slab layouts are pre-allocated into caches. Whenever the kernel requires a new data structure, space for the data structure is simply taken from the slab cache. If the slab cache starts to run out of a certain slab layout, it automatically provisions extras. Graphically, slabs can be represented in a manner shown here. In this example, we have two pre-allocated copies of the same slab layout, in which each slab can hold a single instance of each of 5 different kernel objects. Some wasted memory does occur with this arrangement, since there might be a larger number of one type of object than of another type of object. However, this approach is generally more efficient in terms of kernel space utilization. Slab allocation does require more CPU power than does a classical method, such as first fit. Thus, in some embedded environments, the slab allocator might be preferable. If slab allocation is chosen over the slab allocator, the Linux kernel has two choices of slab allocator. The first choice is the original slab allocator, which was the default allocator until kernel version 2.6.23. This allocator performed well on shared memory systems with few CPU cores, but wasted considerable memory space when used on extremely large shared memory systems, such as those found in graphics rendering farms. To reduce the space waste on large-scale SMA systems, Christoph Lamater at Silicon Graphics developed a new allocator called SLUB, which reduces the size of data structures needed to track allocated and free objects. The initial implementation of the SLUB allocator contained a performance bug that affected the results of certain memory benchmarking tools. Initially, Christoph believed the bug was of little importance, since the conditions required to trigger it were fairly uncommon in practice. However, Linus informed Christoph that either the problem would be fixed, or SLUB would be dropped entirely from the kernel. In the end, it was determined that the bug was caused by adding partially used slabs at the beginning of a linked list instead of to the end of that list. The fix was a change to one line of code, and the SLUB allocator has been the default Linux allocator since 2.6.23.
In this lecture, I will introduce paging and related topics, including logical addressing, address translation, and the translation look-aside buffer. Paging provides a mechanism for sharing memory among multiple user space processes at the same time. This mechanism improves upon simpler algorithms, such as static partitioning and direct power of 2 methods, by allocating fixed-size pages of memory to processes. Key to effective memory utilization with paging is that each process is given its own logical memory space. In other words, each process has its own view of memory with its own address space. The addresses that the process sees are called logical addresses. These logical addresses are divided into fixed-size pages. Each process in the system receives its own private set of pages with private memory addresses. When a process accesses memory using one of its logical addresses, the CPU translates the logical address into a physical address. Physical addresses refer to locations in system memory. For performance reasons, translation is done in terms of memory frames, or fixed-size regions of RAM. Base frame size is normally 4 kibibytes, although this can vary by hardware device, and most hardware can support multiple different frame sizes. Operating systems normally use logical page sizes that correspond to supported hardware frame sizes. Again, 4 kibibyte pages are a typical base size. On x86 and x86-64 systems, the Linux kernel can support so-called huge pages, which can be as large as 1 gigabyte when using the newest AMD and Intel CPUs. The key advantage to paging is that it eliminates the issue of external fragmentation. Since the CPU is translating logical page-based addresses into physical frame-based addresses anyway, there is no need for the physical frames to be contiguous. As a result, we can store a data structure in process memory using pages that are logically contiguous. However, when these logical pages are mapped to physical frames, the frames may be scattered throughout RAM. Notice that the distinction between a page and a frame is a matter of terminology. A page refers to a block of logical memory, while a frame refers to a block of physical memory. For now, pretend that there is a one-to-one correspondence between logical pages and physical frames. We'll make things more complicated later. The key to making page translation efficient is that the CPU contains special hardware called the Memory Management Unit, or MMU, which performs the translation operations. In this diagram, the process accesses memory using logical addresses, which are divided into pages. When requests are made using these addresses, the Memory Management Unit on the CPU translates the logical address into a corresponding physical address. The resulting physical address will be to some point of a physical memory frame. Note that individual memory addresses within pages or frames still remain contiguous, which is important because the MMU translates page numbers to frame numbers, leaving the offset to the memory location within the page unchanged. As shown in this diagram, we can divide a logical address from a process into 2 components, the page number P and the offset D. When the MMU is asked to perform a translation, it consults a data structure called a page table, which provides a mapping between page number and frame numbers. Using this information, the MMU constructs the physical address by using the corresponding frame number, represented here by the letter F, in place of the page number. Once again, the offset to the particular byte within the page or frame is left unchanged. A particular byte in RAM is actually addressed using the frame number and offset in the frame. However, to the process, this memory access appears to occur using a logical memory address, which is conceptually divided into a page number and offset. The offset component is not changed by the MMU, but the page number is replaced by the physical frame number. In order to perform the translation from page numbers to frame numbers, the MMU must consult the page table. The page table is a data structure that is itself stored in RAM in the kernel memory space. Storing the page table in RAM leads to a major problem, since every MMU translation would require a lookup. As the lookup requires a memory access, each process memory request would actually require 2 physical memory accesses. This situation is especially troublesome because a memory access occurs both upon accessing data and upon reading the next instruction to be executed. Without some additional hardware to resolve this problem, system memory performance would be effectively cut in two, greatly reducing the overall performance of the system. The solution for eliminating the double memory access issue is to add a component to the CPU called the Translation Look-Aside Buffer, or TLB, which stores some page-to-frame mappings. Some TLBs also provide room for address space identifiers, which aid in implementing memory protection. The TLB is a piece of associative memory, meaning that it can perform rapid, parallel searches, resulting in constant time lookups for page translation. This memory is exceptionally fast, meaning that it is also quite expensive. As a result, TLB sizes are typically limited from 8 to 4,096 entries. The addition of the TLB provides a potential shortcut for performing address translation. Instead of immediately searching the page table, the MMU first searches the TLB. If the page-to-frame mapping can be found in the TLB, then it is used to perform the translation from page number P to frame number F. This situation is called a TLB hit. A TLB miss occurs whenever the page number is not present in the TLB. In this case, the MMU must search the page table to locate the appropriate frame number. The CPU and operating system employ various policies to determine when to store a page-to-frame mapping in the TLB. A simple policy would be to use a first-in, first-out policy that replaces the earliest entry in the TLB with the newest entry upon a TLB miss. Other, more complex, and potentially better policies also exist. Page tables are data structures that store mappings between logical pages and process memory and physical frames in RAM. These structures are used and managed in different ways on different systems, often with assistance from the hardware. At the end of this lecture, I will discuss extended page tables, which are useful for allowing hardware to support multiple simultaneous operating systems at once. Recall from the previous lecture that the page table stores mappings between page numbers and frame numbers. Whenever a TLB miss occurs, the page table must be searched to find the appropriate mapping. CPUs have differing levels of support for managing and searching the page tables automatically. On most modern systems, including x86-64 and ARM CPUs, page tables are managed and searched by the CPU automatically upon TLB miss. This search increases the memory access time, but no fault or interrupt is generated. As a result, the CPU does not have to perform a context switch. Among a few other CPUs, the MIPS architecture requires the operating system to manage and search the page table. Whenever a TLB miss occurs, the CPU triggers a fault, which is a type of interrupt. The CPU must make a context switch away from whatever task is currently being executed in order to execute the interrupt handler for the fault. Software-managed page tables are becoming increasingly uncommon even on embedded systems, as the popular ARM CPU supports hardware management. The MIPS CPU is typically used in lower-end consumer devices, such as inexpensive e-readers and the least expensive tablets. One approach to reducing the page table search time whenever a TLB miss occurs is to store the page table as a tree instead of a list. This technique of hierarchical page tables divides the page tables into pages. Each logical address in process memory is divided into an outer page table, a set of offsets into various levels of subtables, and a final offset to the specific byte of memory to be accessed. This technique can be generalized to any number of levels in the hierarchy, but I will present here a simple system that uses only 2 levels. As illustrated in this diagram, data structure is arranged so that an outer page table provides a mapping between outer page numbers and page table pages. Once the proper page table page is located, the translation from page number to frame number can be completed quickly, since the page of the inner page table is relatively small. The address translation mechanism used with hierarchical page tables is more complex than that used with a simple linear page table. The logical address is divided into additional components. In this example, with 2 levels in the page table,
the logical address is divided into an outer page table entry number, T, which specifies the location in the outer page table in which to find the proper inner page table. The next component of the address, P, is the offset into the inner page table at which the mapping can be found. In this example, we have a single page-to-frame mapping in each inner page table entry, so we can obtain the frame number from that entry. A real system will be more complex and likely will require a short linear search at some level of the page table. Once the frame number is determined, RAM is accessed in exactly the same way as it is in simpler designs, with the final address joining a frame number and offset into the physical address. Storing the page table in a tree improves access performance. However, as the total amount of system RAM continues to increase with newer and newer generations of computers, the size of the page table also increases. Moreover, the address spaces on 64-bit architectures are much larger than the amount of memory that the MMU actually supports. Current 64-bit systems have true hardware address sizes in the range of 34 to 48 bits. If we were to store a mapping to handle every logical page number in such a system, the mapping would be large and inefficient, since the address space is sparse. That is, not every 64-bit logical address can map to a physical location in RAM, since the physical addresses are at most 48 bits. As a result, many of the possible 64-bit addresses are unused. The solution to this problem, which both reduces page table storage size and increases search speed, is to use a hash table or dictionary structure to store the outer page table. Since several addresses may hash to the same value, each entry in the hash table is an inner linear page table, which allows the hash collisions to be resolved through chaining. Translating a logical address to a physical address with a hashed page table begins by hashing the page number P. Hashing is accomplished using a hash function, which may be implemented in hardware for high performance. The hash value returned by the function gives the location in the hash table where the inner page table may be found. A linear search of the inner page table is performed to locate the frame number. Once the frame number, F, is obtained, it is joined with the offset, D, to give the hardware address. Some architectures, notably PowerPC and Intel Titanium, store their page tables backwards. That is, the system stores a data structure with one entry per frame, and the entry stores the corresponding page number along with the process ID of the process under the page. This approach, called an inverted page table, is efficient in terms of page table storage size. However, inverted page tables are inefficient in terms of performance, and these structures are not used on the majority of systems. On newer x86-64 systems with virtualization extensions, hardware support exists for extended page tables, or EPT. AMD and Intel each brand this technique with a different name. AMD uses the term Rapid Virtualization Indexing, or RVI, on newer CPUs. They used to call this technique nested page tables, or NPT. Intel uses the extended page tables terminology. EPT adds a level of paging to the system. At the outer level, each virtual machine, or guest, running on the CPU sees its own set of memory frames, isolated from and independent of the actual hardware. The CPU translates page numbers to frame numbers, first by translating the page number to a guest frame number. The guest frame number is then translated to a host frame number, which is the physical frame number. EPT technology is important for virtual machine performance, since it allows each guest to manage its own memory efficiently. Moreover, guests can access memory without having to switch the CPU into hypervisor mode, which can be an expensive operation. The downside to logical address translation with extended page tables is that it becomes conceptually more difficult to understand, as illustrated by the complexity of this diagram. A process running in a guest operating system makes a memory request just as it would if no virtualization were present. This memory request is divided into a page number and an offset as usual. The CPU then performs translation of this page number, P, to a frame number, F, also as usual. Furthermore, as far as the guest operating system is concerned, the translation is complete. The guest OS sees the memory region provided by the host system as if that memory were physical memory. In other words, the guest OS has no idea that it's running in a virtual machine. To the guest OS, the virtual machine looks just like a physical system. However, in reality, the guest's physical memory is actually an illusion provided by the host. To make this illusion work, the host must translate the frame number, F, in guest memory to an actual physical frame number, G. This translation is performed by the CPU without any context or mode switches using the EPT table. Once this translation is performed, the physical memory address is generated by combining G and D, where D is the original, unchanged offset into the page. It is important to note that this entire process is performed by the CPU without switching to the host OS or hypervisor. In this lecture, I will discuss memory protection, including segmentation and permission bits on page table entries. Remember that operating systems perform two functions, abstraction and arbitration. Mechanisms for accessing memory provide abstractions of the underlying memory hardware. However, operating systems must also arbitrate access to RAM by ensuring that one process cannot access memory that does not belong to it. Without this arbitration, a process could change memory belonging to another process, or worse, it could crash the system by changing memory that belongs to the kernel. On systems that utilize simple memory management, such as power of two methods, memory access protections are provided by a mechanism called segmentation. On the majority of modern systems which employ paging, memory protection is implemented as part of the paging system, and memory access permissions are stored in the page table. On any system, process memory is divided into logical pieces or segments at compile time. These segments include the text segment, a region for global variables, a stack region for automatic variables, and a heap for dynamically allocated data structures. Access permissions apply to each segment. In particular, the text segment is set to be read-only. Outside a single process, there must be a mechanism to track which segments of memory belong to which processes. When a process is executing, its segments are marked valid so that it can access the corresponding memory locations. Segments of memory belonging to other processes are marked invalid, and any attempt to access those segments results in a fault or interrupt called a segmentation fault. Typically, a segmentation fault causes the process to be terminated. Segment memory permissions are implemented on non-paging systems using a segment table. The segment table has permission bits that can be applied to each region of memory. When memory is accessed using segmentation, the segment table must be consulted to determine whether or not the access is legal. In this example, a process requests access to memory using a logical address. Since we do not have paging with this system, this logical address is not translated by a page table mechanism. However, this logical address is divided into a segment address and an offset into the segment in a manner similar to page translation. The MMU checks the segment table to determine if a particular memory access is valid. In this example, the segment table stores up to 4 permissions and up to 3 bits, a valid-invalid bit, a read-write bit, and an execute bit. In practice, most systems that support segmentation without paging normally only use 2 bits, valid-invalid, and read-write. If the process tries to read from a segment that is marked valid, memory access is permitted and occurs normally. The same thing happens if a process tries to write to a memory location that is marked both valid and writable. However, if a process tries to write to a segment marked read-only, or if a process tries to access an invalid segment, the CPU triggers a segmentation fault and the process is terminated. For some invalid accesses on a Unix-like system, this segmentation fault may be reported as a bus error. With paging systems, which comprise the majority of modern systems, including mobile devices, Memory protection is accomplished by adding permission bits to the page table entries. In general, page table entries will have a valid-invalid bit and a read-write bit. The valid-invalid bit is used in the same way as it is for segmentation. Pages that a process is allowed to access are marked valid. Other pages and any non-existent pages are marked invalid. If a process attempts to access an invalid page, a CPU fault is raised, which functions like an interrupt to trap into the kernel. A Linux kernel will send a SIG-SIG-V or SIG-bus signal to the process, depending on the location and memory the process tried to access. In practice, this signal is normally not caught and the process terminates. For historical reasons, this event is called a segmentation fault, or seg fault for short. The read-write bit, used to mark the text segment of a process, can be used to allow pages of memory to be shared between processes. Pages that are reentrant or read-only can be accessed by multiple instances of multiple programs simultaneously. This capability is useful on modern systems since multiple instances of programs are typically run at the same time. In the case of a web browser, for example, it is only necessary to load one copy of the browser program code into memory. Several copies of the browser can be run as several different processes, sharing the program code and thus saving memory. The open source Chromium browser and its Google Chrome derivative allow each tab to run in a separate process. Shared memory pages allow the code for the browser, any extensions, and any plugins to be loaded only once, saving memory. This diagram illustrates how two processes can share a single page in RAM. Each process sees a handful of valid frames, one of which is marked read-only. If this memory frame contains code or other information that can be shared between the processes, then the two frame numbers will be identical within the separate processes. Each process may use a different page number to represent this memory location, however, since each process has its own independent, logical view of memory. Incidentally, this diagram is a conceptual diagram only. It does not directly map to any particular data structure in the operating system. Instead, the two tables illustrate how each process might see the page table. Newer AMD and Intel CPUs support an additional permission bit for setting execute permissions. This bit, called the no execute or NX bit, is actually an inverted permission. It is set to 1 whenever execution of data found on a memory page is forbidden. Originally, the NX bit was implemented by AMD on its 64-bit capable processors, using the marketing name of Enhanced Virus Protection. Intel followed suit and added this mechanism as the execute disable or XD bit. The concept behind the bit was to provide a mechanism that could be used to prevent execution of native machine instructions from memory space used for regular data. Although the primary beneficiary of this feature was a certain virus-prone system that is not a Unix variant, the Linux kernel does support the NX bit as a guard against buffer overflow and similar exploits. In the example presented in the hypothetical page table here, only the page with hex numbers 04A4 allows code execution. In the event of an exploit attempt, a malicious application could try to load code in another page, perhaps 04A1. However, since the NX bit is set on that page, any attempt to execute the code loaded by the exploit will trigger a CPU fault, and the process will be terminated. This mechanism increases the security of the system against certain types of attacks.
In this lecture, I will begin discussing virtual memory. Due to the complexity of the virtual memory subsystem, the second part of this introduction will be given as a second lecture. We have previously seen that each process in the system can be given its own logical memory space. This arrangement allows logical pages to be mapped to physical frames without the need for physical frames to be contiguous, eliminating external fragmentation and increasing the degree of multi-programming that the system can support. We can further increase the degree of multi-programming in the system by recognizing that processes do not actually use all the memory in their logical address spaces at any given time. Parts of the program code, including error handlers and infrequently called functions, are not utilized often. Furthermore, arrays and other data structures are often oversized and used in sections instead of all at once. If we can swap unused pages out of memory and onto a backing store, such as a hard disk, we can fit more processes into memory at once, increasing our degree of multiprogramming. Furthermore, we can give each process its own large logical memory space, which can in fact be larger than the amount of physical RAM on the system. When we add a backing store, the general address translation process remains the same. Processes access memory using logical addresses, which are translated into physical addresses by the MMU. The page table is still utilized to store the page-to-frame mappings. However, we do add some complexity in that a frame could be swapped out to disk at the time when it is needed. The CPU must provide a mechanism to detect the situation and generate a fault that the operating system can handle to bring the required page back into physical memory. The process of moving pages or frames of memory back and forth between RAM and the backing store is known either as swapping or as paging. Historically, the term swapping referred to the movement of entire logical address spaces or entire processes between RAM and disk. Moving single pages or frames of data between RAM and the disk was called paging. In modern practice, both terms are used interchangeably, and the Linux kernel component that performs page movements is called the swapper. A single movement of a single page frame into or out of physical memory is called a page swap. Historically, Linux machines used a dedicated hard disk partition to store the pages that were swapped out to disk. Modern versions of Linux are just as efficient using a swapped file, which is a regular file stored alongside other data in the file system. It should be noted that swapping is an optional feature, and it is possible, and even quite common, to run systems without any backing store or swapping capability. Most embedded Linux systems, such as Android devices, do not use a backing store. If memory cannot be allocated to a process on such a system, the process typically crashes. Now, page swaps are implemented by the operating system. Some assistance from hardware is required to determine when a page swap needs to be performed. When translating a page number to a frame number, the MMU checks to see if the corresponding frame is resident or loaded in RAM. If the frame is present, the memory access proceeds as normal. If the frame is not present in RAM, however, the MMU generates a page fault, which is a CPU exception that is similar in concept to an interrupt. A specific page fault handling routine is registered with the system, either as part of the interrupt vector table or using a separate structure for fault handlers. A page fault causes this routine, known as the swapper in Linux, to be invoked. It is then the responsibility of the swapper to locate the missing page on the backing store and load it into RAM, possibly moving some other page frame to the backing store in the process. The address translation process gains a few steps when paging is utilized. A process makes a memory request using a logical address in its private address space as usual. The MMU first checks the translation look-aside buffer to determine if the page-to-frame mapping is present. In the case of a TLB miss, the MMU must consult the page table to find the mapping. Once the mapping from page number to frame number is known, the MMU must next verify that the page is actually loaded in physical RAM. If the corresponding frame is available in RAM, the memory access proceeds as normal. However, if the corresponding frame is not in memory, the MMU generates a page fault, which is essentially a type of interrupt. If generated, the page fault causes the operating system to switch context to the page fault handling routine, which retrieves the corresponding memory contents from the backing store. Once this process is complete, the OS changes the CPU context back to the original process, and the memory access proceeds as normal. In order for the MMU to be able to detect situations in which a requested memory frame is not physically present in RAM, an extra bit must be added to the page table. This bit is set to 1 whenever the contents of a logical page are present in a memory frame. If the present bit is 0, the page has been swapped out to the backing store. For efficiency reasons, the TLB entry corresponding to a row in the page table must also store the present bit. You might have noticed that the terminology between page and frame is starting to become a bit blurry here. In general, we refer to pages of memory being swapped out to disk, even though the swap operation is actually moving physical memory frame contents. This fuzzy terminology is a result of historical evolution of the virtual memory subsystem. Now, I'd like to take a moment to discuss the nature of backing stores as technology is changing in this area. Historically, the backing store was a mechanical hard disk drive, and a number of design decisions in the virtual memory subsystem still use this assumption. However, many systems now, especially embedded systems, have only solid-state storage. Since each block on a solid-state drive can be erased and written only a finite number of times, there is some question as to whether it is a good idea to use an SSD as a backing store for virtual memory. Many embedded devices do not use paging for this reason. Another issue with the backing store is that it is subject to attack via forensic disk analysis methods in the event the device is lost or stolen. Sensitive information, such as cached passwords and other credentials, might have been swapped out to the backing store, and these pieces of information could be recovered. One solution to this problem, which is available as an easy-to-enable option in Mac OS X, is to encrypt the contents of virtual memory. The downside to this approach is the addition of CPU overhead on top of the generally slow nature of the backing store hardware. Another approach to avoiding the issues of write limits and post-mortem forensic recovery of sensitive memory data is to use the Linux compressed caching, or comp cache, mechanism as a backing store. With this approach, a section of RAM is reserved ahead of time to create a compressed RAM disk, or ZRAM disk. When a page is swapped out to this ZRAM disk, it is compressed on the fly to fit into a smaller amount of memory. Whenever a page needs to be swapped in from the backing store, the page is read from the ZRAM disk and decompressed. Although the compression and decompression steps do result in CPU overhead, the comp cache system is still generally faster than using a disk or SSD as a backing store. Furthermore, comp cache is as secure as RAM against forensic analysis, particularly against recovering sensitive information from a system that has been powered off for a period of time. In this lecture, I will continue the discussion of virtual memory by discussing paging performance and introducing demand paging, copy on write, memory mapped files, and shared libraries. Swapping pages to and from a backing store is a relatively slow operation compared to a direct access to RAM, due to the fact that most backing store hardware is several orders of magnitude slower than RAM. Whenever a page fault occurs, the memory access that triggers the page fault will require more time than a non-faulting memory access. As long as the number of pages swapped out to the backing store is relatively small compared to the total number of pages of memory in the system, the performance cost of page swaps is amortized over all memory accesses. As a result, the average memory access time is increased by only a small amount relative to a system that does not swap out pages. However, if the fraction of memory accesses resulting in page faults becomes too high, the system begins swapping, or thrashing, its memory on most or all memory accesses. This situation typically occurs when memory becomes oversubscribed due to a program bug, and the result is a system that is painfully slow to respond to user input. In some cases, on some systems, the OS may need to be rebooted to recover from a swapping situation.
With any paging system, it is necessary to decide on a virtual memory fetch policy, which determines how data are loaded into memory pages for the first time, typically when a program is started. A lazy implementation of page fetching is to use demand paging, which loads a page from the backing store into RAM only when it is actually required. This approach improves the overall responsiveness of the system and increases the degree of multiprogramming at the expense of reducing the initial performance of newly started processes. The main alternative to demand paging is prefetching, which loads some pages into memory before they are actually needed. Prefetching may waste some memory by loading data that will not be used. However, it does improve the startup performance of many software applications. For this reason, prefetching is a fairly common feature of desktop operating systems. When memory is limited, or electrical power is severely limited, a pure demand paging approach to fetching may be appropriate. Pure demand paging does not prefetch any pages, including the text segments of newly started programs. When a new program starts, a page fault occurs at the first instruction, and the first page of the program code is loaded into memory. Pure demand paging has the greatest potential to increase the degree of multiprogramming, particularly in situations where physical RAM is extremely limited. In addition, the lack of prefetching can save CPU and memory operations, thus providing a small power savings when operating from battery. As such, pure demand paging could be useful on smaller embedded systems, especially monitoring devices and other systems without direct human interaction. While the fetching policy has a high impact on newly started programs, a copy-on-write approach improves performance whenever a process makes a copy of itself. On Unix-like systems, new processes are created when a running process clones itself with the fork system call. Cloning all memory at fork time could be a slow operation, since a process might be using a large number of pages. Copy-on-write addresses this performance issue by having the clone initially share the original process's memory pages. These shared pages are marked read-only, causing the MMU to fault if either process tries to write to them. The operating system handles this type of fault by copying the page and turning off the read-only bits on both the copy and the original page. This diagram illustrates the copy-on-write process. In the top half of the diagram, the original process forks a child process, which initially shares the original parent's pages. The child proceeds to modify page 3 in the bottom half of the diagram. When this modification is attempted, the MMU raises a fault that traps into the operating system. The operating system makes a copy of the corresponding memory frame, gives the copy to the child process, and removes the read-only setting on both the original and cloned page. The child's page is then updated with the modified value from the memory write, and normal process execution resumes. In addition to increasing the degree of multiprogramming by enabling pages of memory to be swapped out to a backing store, the virtual memory subsystem can also be used to improve I/O performance for processes on the system. When programs request I/O from persistent storage devices, these requests generally take a significant amount of time to fulfill due to the relatively slow speed of the persistent storage device. Since many processes perform frequent reads and writes of small pieces of data, the performance overheads caused by waiting for device I/O to complete can become substantial. The virtual memory subsystem can be made to reduce this overhead by memory mapping files. Page-sized pieces of a file are loaded into memory where they can be read and written efficiently. These pages are periodically written back to the persistent storage device. As is the case with paging in general, there is no requirement that memory-mapped files be mapped into contiguous regions of physical memory. Logical addressing is used to present an ordered, contiguous, logical view of the file to the process. However, the file may be mapped out of order in non-contiguous memory frames. Although the file will be put back in order when it is stored to disk, the file still might be non-contiguous if the file system is fragmented. To reduce the total amount of memory required by a program, and to make software development easier, certain programming routines are implemented in shared libraries, which can be used by multiple programs on the system. When these libraries are used by a program, they must be made available to the program when it runs. In the simple case, which defeats the memory-saving potential of shared libraries, the compiler may statically link or copy the library into the program executable at compile time. A more efficient approach is for the loader to link the program to the shared library at runtime. On disk, precompiled shared libraries are stored in binary form as shared objects or .so files on Unix. These libraries are called dynamic link libraries or DLLs on Windows. Runtime dynamic linking of these shared libraries relies on read-only shared pages that can be used by multiple programs at the same time. Shared libraries are made available to processes by mapping them into the middle of the logical address spaces of each process, between the stack and the heap. These shared objects limit the maximum size to which the stack or heap can grow before running out of space. A situation in which shared library mapping becomes a problem is when virtual machines are implemented on 32-bit hosts. The hypervisor process on these hosts has a maximum logical address space of 4 GB. When the hypervisor tries to allocate a large contiguous block of memory to provide RAM to the guest system, the allocation could run into the shared libraries, resulting in failure. I have seen this type of failure occur on a 32-bit host when trying to allocate a contiguous block of just over 1.2 GB on a Linux system with 4 GB of physical RAM. It is for this reason that a 64-bit operating system is desirable even for physical systems with only 2 to 4 GB of RAM. Lecture, I will discuss page replacement as it is used in the virtual memory subsystem. I will discuss global and local page replacement, page table entries that support page replacement, and a number of classical page replacement algorithms. Whenever there is a demand for memory that is greater than the actual amount of physical RAM installed on the system, the operating system must determine which pages will be kept in memory and which pages will be swapped out to disk. When memory frame contents are swapped out to disk, the operating system needs to find a page of memory that is not currently in use. Furthermore, in an ideal case, the operating system should also pick a page that will not be used for some time, so as to reduce the total number of page swaps. In order for the page swapper to operate, some additional data must be kept about each page, including whether or not the page has been referenced and whether or not the page has been altered since it was last swapped into RAM. Decisions regarding page swaps can be made globally or locally. With global replacement, any page in the system is a potential candidate to be swapped out in favor of another page. While simpler to implement, global page replacement does allow processes to steal memory frames from each other. On the other hand, local replacement policies allocate a limited number of frames to each process. When a process exceeds its frame allocation, only frames belonging to that process are selected for replacement. Implementing a local page replacement algorithm is more complex than it seems on the surface, largely due to Bellidy's anomaly. Allocating more frames to a process does not necessarily reduce the number of page faults that occur as a result of that process. In fact, with some replacement algorithms, increasing the number of available frames actually increases the number of page faults that occur. At the opposite extreme, allocation of too few memory frames to a process also increases the number of page faults. Without enough physical memory, processes will spend more time page faulting or swapping than they will spend executing. The goal with a local replacement algorithm is to find an optimal working set for each process. This working set is the minimum number of frames that a process actually requires in order to execute to some desired level of efficiency. Regardless of whether global or local replacement policies are chosen, the operating system needs a few pieces of information to implement page swapping correctly. First, the operating system needs to know whether or not a page that is currently in memory has been referenced by a process. Pages that are loaded but unused might be more ideal candidates to be swapped out to the backing store. The second piece of information that needs to be stored in the page table is the dirty bit. This bit is set to 1 whenever a process writes to a page, which lets the operating system know that the copy of the memory frame contents on the backing store needs to be updated whenever the page is swapped out. Keep in mind that on systems with hardware-managed page tables, such as the x86 and x86-64 platforms, the MMU updates these bits automatically. Whenever a page fault occurs, the operating system must locate the desired page on the backing store. Then it must find a free frame in RAM into which the page can be loaded. If no memory frames are free, the operating system must select a victim frame to be swapped out to the backing store. The algorithm that is run to determine which frame will be the victim is called the page replacement algorithm. Page replacement algorithms ideally should minimize the total number of page faults in the running system in order to maximize system performance. Let's take a look at several classic page replacement algorithms. The first classical page replacement algorithm we will consider is the random algorithm. Whenever a page swap is required, this algorithm simply picks a victim frame at random. In practice, this random selection often picks a page that will be needed in the near future, leading to another page fault in a short time period. As such, it is not effective for minimizing page faults. Another ineffective algorithm is to select the oldest page, or the page that has been in memory for the longest period of time. Unfortunately, this page could be frequently accessed, so if it is swapped out, another page fault could be triggered in a short period of time to bring it back into memory. Somewhat counterintuitively, selecting the frame that has been accessed the least frequently is also ineffective. A page that is used relatively infrequently might still be used regularly, which would lead to another page fault to bring this frame back into RAM. The most frequently used algorithm picks whichever frame is being used the most and selects that frame to be swapped out to the backing store. This is a completely stupid idea, since this page is likely to be accessed again shortly after it is swapped out. A good algorithm for choosing victim frames is the least recently used, or LRU algorithm. This algorithm selects the victim frame that has not been accessed for the longest period of time. Unfortunately, with current hardware, there is no good way to track the last memory access time. Tracking every access in software would be a terrible idea, since such a scheme would require an interrupt on every memory access. Thus, it is impractical to implement LRU directly. Most implemented page replacement algorithms are approximations of LRU, however. Theoretically, the optimal algorithm, or opt, is the best page replacement algorithm to use. With this algorithm, the operating system picks a frame that will not be accessed for the longest period of time as the victim, delaying a future page fault related to the corresponding page for as long as possible. A mathematical proof exists showing that opt is the best possible page replacement algorithm. Unfortunately, opt is also impossible to implement, since it must be able to predict all memory accesses ahead of time. As such, we are left with LRU approximation algorithms, such as the not used recently, or NUR algorithm. NUR tracks frame accesses using a combination of the reference bit, dirty bit, and/or an age counter. This algorithm produces reasonable performance in actual implementations. In this lecture, which is presented in two parts, I will begin discussing processes. I will introduce the process model, discuss the type of information associated with a process, give an overview of process state, and introduce the concept of process forking. As is usually the case, my presentation is focused on Unix-like systems. Let's begin by defining what a process is. A process is an instance of a computer program in execution.
When we ask a computer system to run a program, the code for that program is loaded from disk into memory and executed as a process in the system. On some platforms, processes might be called jobs or tasks. On a modern system, a process consists of one or more threads of execution. In other words, a process can execute one instruction at a time, or it can execute several instructions at the same time on the CPU. Each process on the system receives its own private allocation of resources. Each process also has access to its own data, and the operating system maintains statistics about each process in order to make effective scheduling decisions. In memory, a process is divided into segments. Program code and other read-only data are placed into the text segment. Global variables in a program have their own data segment that allows both reading and writing. Automatic variables, or local variables and functions, are allocated at compile time and placed on the stack. Data structures explicitly allocated at runtime are placed on the heap. As memory is used by a process, the stack and the heap grow toward each other. If a process makes use of shared libraries, these libraries are mapped into process memory between the stack and the heap. In order to track processes correctly and allow multiple processes to share the same system, the operating system must track some information that is associated with each process. This information includes the memory that the process is using, as well as the current location in the process code that is executing, known as the process program counter. The operating system must also track other resources in use by a process, including which files are currently open and any network connections the process is using. In addition to the information generated by the process itself, the operating system must keep scheduling information and statistics about each process. This information includes a unique identifier, or process ID, that can be used to distinguish processes from each other. In order to arbitrate access to system resources, the operating system must also store information about the owner of a process so that permissions can be enforced correctly. To facilitate scheduling decisions, the operating system collects various statistics about process execution, such as the amount of CPU time consumed and the amount of memory used. During the lifetime of a process, the process moves between several states. When a process is first created, it is initially in the new state. Once creation is complete and the process is ready to run, it transitions to the ready state where it waits to be assigned with CPU core. When the scheduler selects a ready process to run, that process is moved to the running state and is given CPU resources. During execution, a process might request external resources such as disk I/O. Since these resources take time to provide, the process is moved out of the running state and into the waiting state so that the CPU core can be given to another process. Finally, when a process is finished, it is placed in the terminated state so that the operating system can perform cleanup tasks before destroying the process instance completely. In this diagram, we can see how processes may transition between states. At creation time, a process is placed into the new state while the operating system allocates initial memory and other resources. Once creation is complete, the process is submitted to the system and placed in the ready state. Whenever a CPU core is available to execute a process, it is dispatched to the running state where it executes. Execution of a process can be interrupted for a variety of reasons. If a hardware interrupt occurs, the operating system might have to move the process off the CPU core in order to service the interrupt, returning the process to the ready state. Or the process might make an I/O request, in which case the process is moved to the waiting state while the system waits on the relatively slow I/O device to provide the requested data. Once I/O is complete, the process is moved back to the ready state so that it can be scheduled to run again whenever a CPU core becomes free. Upon exiting, the process is moved to the terminated state for cleanup. The mechanism for process creation is platform dependent. I will be introducing process creation on a Unix-like platform such as Linux or Mac OS X. On these platforms, all processes descend from a single parent process that is created by the kernel at boot time. On Linux, this first process is called init, which is the common Unix name for the first created process. Apple decided to call this process launchd on Mac OS X. By convention, the initial process always has a process ID of 1. The initial process must also remain alive for the entire time the system is up and running. Otherwise, the whole computer crashes with the kernel panic. The init or launchd process is started by the kernel at boot time. Every other process on the system is a child of this special process. Child processes on Unix are created by forking the parent process. The parent process makes a system call named fork, which makes a copy of the parent process. This copy, which is initially a clone of the parent, is called the child process. It is up to the parent process to determine what, if any, resources it will share with the child process. By default, the parent process shares any open file descriptors, network connections, and other resources apart from the CPU and memory with the child. However, the program code can close or reassign resources in the child, making the child completely independent of the parent. Once a child process is forked, the child becomes an independent instance of the program, which can be scheduled to run in parallel with the parent. However, the parent process can be coded to wait on the child process to finish executing before the parent proceeds. Furthermore, the parent process is able to terminate the child process at any time. On some systems, termination of the parent process will terminate all child processes automatically. On other systems, child processes become orphan processes whenever the parent terminates. Unix-like systems, including Linux, have the ability to support both models. Any process, including a child process, has the ability to load a different program into its memory space. This loading is accomplished via the exec system call, which replaces the entire program code of the process with the program code from a different program. New programs on Unix-like systems are started by forking an existing program, then execing the new program in the child process. When multiple processes are executing on the same system, they have the ability to execute independently or share information between themselves. An independent process is completely separate from other processes in the system. Its execution is not affected by other processes, and it cannot affect other processes as long as the operating system is designed and implemented correctly. Alternatively, processes can share information between themselves and thereby affect each other. When this occurs, we say that the processes are cooperating. Cooperating processes may be used for a variety of reasons, including information sharing, high-performance parallel computation, increasing the modularity of a program implementation, or simply for convenience when implementing certain designs. In part 2 of this lecture, I will provide additional detail about process forking and executing new programs. In this lecture, I will continue the discussion of processes by introducing the fork, exec, and wait system calls. I will provide examples of using these system calls in both C and Python. Processes are created on Unix-like systems, such as Linux, by using the fork system call. This call is available as a C function by including the unistd.h header file. In Python, access to fork is provided by importing the OS module. In this C example, I fork a child process that simply prints a message. My code begins by importing the stdio.h and unistd.h header files for the printf and fork functions, respectively. Inside my main function, I declare a variable named PID of integer type. I then print a message stating that I have not yet forked the parent process. I call the fork function without arguments, and I assign its return value to the PID variable. Upon completion of the fork function, I will have 2 copies of my program running at the same time. In the first copy, where I called fork,
the value of the PID variable will be set to the process ID of the child process. In my child process, the value of the PID variable will be set to 0. My child process prints a message stating that it is the child. My parent process prints a message stating that it is the parent. Both messages will be printed since the value of the PID variable will be 0 only in the child process. However, the order in which the two messages are printed is not guaranteed and may vary between program runs. The equivalent Python code is a bit shorter but looks rather similar, owing to the fact that Python is exposing the underlying C library to us. To use the fork function, I need to import the OS module. I then set the PID variable by calling os.fork in a manner similar to the corresponding C code. Upon receiving this call, the entire Python interpreter process will be cloned. The PID variable inside my script in the parent interpreter process will contain the process ID of the child Python interpreter process. In the child interpreter, the PID variable in my Python script will have the value 0. Since the value of PID is 0 in the child process, the child message will be printed. In the parent process, where the value of PID is not 0, the parent message will be printed. Both messages will appear in the output of the script, but the order of the messages is not guaranteed and may change. While we sometimes fork processes in order to create parallel programs, a more common use of forking is to start another program. We can replace a currently running process with another program by using the exec system call, which is made available through a variety of functions in C and Python. One important thing to remember about the exec system call is that it completely replaces the currently running program with the new program. A common error is to try to put program code after a call to exec in an attempt to perform some other operation after the external program is finished. However, any such code placed after the call to exec will never execute, since that code gets replaced with the rest of the original program. Now, in practice, the exec system call is implemented as a collection of functions, not as a single function. These functions differ in whether or not they take arguments as a fixed set of parameters or as an array. They also vary by allowing the operating system to search the system path to find the new program, versus requiring the absolute path to the new program to be provided. Furthermore, some of the exec functions allow environment variables to be set for the new program. Regardless of the version of exec that is chosen, a standard convention on Unix-like systems is that the first argument to a newly loaded program is the name of the program itself, exactly as the user entered it. This convention allows a single program to be known in the system by a variety of names, possibly allowing it to implement different behaviors depending upon the name by which it was invoked. As I mentioned, there are quite a few variations in exec functions. In the C programming language, versions with a lowercase l in the name take a fixed number of arguments, where the final argument is always a null pointer of character type. Alternatively, versions with a lowercase v in the name take a vector or array of arguments. If a lowercase p appears in the name, the operating system will search the system path to find the new program. Versions with a lowercase e allow environment variables to be modified. Corresponding Python versions of exec, available in the OS module, follow the same conventions with respect to the lettering. However, it is not necessary to pass a null pointer at the end of the L versions. Now, let's take a look at a simple C application that forks a child that execs the /bin/echo program installed on the system. Nothing has changed about the fork operation. The PID value returned to the child is always 0, while the value returned to the parent is always non-zero. However, in the child, we are now using execl to load the /bin/echo program. Notice that /bin/echo is both the name of the program and the first argument to the program. The message to be printed, hello, follows. Finally, we must terminate the parameter list with a null pointer, which needs to be cast to a character pointer type. When the child calls execl, its copy of the program code is completely replaced by the code for /bin/echo. Thus, the child never prints the final message in the program. The message is thus printed only once by the parent. The Python version of this code is shorter but otherwise similar. There is no need, nor is there any practical way, to pass a null pointer to os.execl at the end of the parameter list. As is the case with the C version of the code, only the parent prints the message at the bottom. The copy of the Python interpreter and script that was created by fork is completely replaced by the call to os.execl with the code for the /bin/echo program. Thus, the child is no longer executing the Python interpreter, and the final line of code is never run in the child. We have seen that we can execute another program using exec. However, what if we would like to take some other action after the other program executes? In that case, we can use a version of the wait system call in the parent to wait for the child to terminate. Before moving to example code for wait, take a moment to note that, in some cases, the parent process may terminate before the child process. On a Linux system, termination of the parent before the child creates an orphan child process. Some programs are intentionally designed to create orphan processes. These programs are engineered to run in the background, performing various system services, and these are known as daemons or service processes. By convention, the word daemon uses its archaic spelling here with an AE in place of the E in the modern spelling. However, the pronunciation is the same. Daemon is incorrect, even though many people mispronounce it. Now, the C code illustrating the act of waiting on a child process to terminate barely fits on one slide. In order to get access to the waitpid function on Linux, I need to include the sys/wait.h header file. In this example, I fork a child process that sleeps for 5 seconds before exiting. In my parent code, I announce that the parent is waiting, then I call waitpid to wait for the child to terminate. In this simple example, I need to pass 3 arguments to waitpid: the process ID of the child, which fork returned to the parent above, followed by a null pointer, followed by the number 0. The waitpid function blocks, or stops and waits, until the child process terminates. Once termination occurs, the parent prints another message. The Python version of this example is considerably shorter, but once again, it uses essentially the same calls. In addition to the OS module, I need to import the time module to get access to the sleep function. The major difference in this code from the corresponding C code is that I do not pass a null pointer as the second argument to os.waitpid. Instead, I skip that argument and simply pass a 0 instead. Discuss process management. I will discuss process context, context switches, and process scheduling. Each process running on a system has a certain amount of information associated with it. A minimal set of state information that allows a process to be stopped and later restarted is called process context. Process context includes the current contents of CPU registers, the current program counter value for the process, and the contents of RAM the process is using. Switching between processes on a system is often called a context switch, although process switch is a more precise term. The operating system can perform a context switch from a process into a section of the kernel and then back to the same process without actually performing a process switch. Context switches require at least one mode switch to perform, since the CPU must enter supervisor mode to enter the kernel. Relatively speaking, context switches are a fairly expensive operation, and frequent context switching will reduce system performance. Whenever the operating system needs to switch from one process to another, it must first make a context switch into the kernel. The kernel then saves the state of the previously running process and restores the state of the process to which it is switching. The second context switch is then required to start the newly restored process. On Unix systems, processes are created via the fork system call. Following creation, the CFQ scheduler determines when and where the process will be run. Once the CFQ core is selected, the dispatcher starts the process. Whenever a process makes an I/O request, a system call into the kernel is made, which removes the process from execution while waiting for the I/O to complete. The process yields any CPU cores it is currently using, so that another process can use those resources while the first process waits on the relatively slow I/O device. Operations that cause the process to yield the CPU cores and wait for some external event to occur are called blocking operations. Reading data from a file is an example of such an operation. The process calls the read function, and the read function does not return until it has read some data. The process may have been moved off the CPU and then restored and returned to the CPU while waiting for the read function to return. Some processes are CPU bound, which means they perform large computations with few I/O requests or other blocking operations. In order to enable the system to service other processes and effectively implement multi-programming, the CFQ scheduler must preempt these types of processes. Preemption involuntarily saves the process state, removes the process from execution, and allows another process to run. Interrupts from hardware devices may also preempt running processes in favor of kernel interrupt handlers. Without this type of preemption, the system would appear to be unresponsive to user input. Now, in order to store process state information, the operating system must maintain data structures about each process. These structures are called process control blocks, or PCBs. PCBs contain fields where information about a process can be saved whenever a process is moved off the CPU. Once again, this information includes the contents of CPU registers and current program counter value. The operating system stores process control blocks in linked list structures within kernel memory space. Here is a process control block in greater detail. Some of the information fields include process state, the unique ID for the process program counter, CPU register contents, memory limits for regions of memory used by the process, open file descriptors, and other data. When performing a process switch, it is critical that the operating system saves the process's CPU state. At a theoretical minimum, this state information includes the program counter and CPU register contents. In practice, more information will be saved during each process switch. This diagram presents a simplified view of process switching, where only the program counter and register contents are saved and restored. Here, the operating system switches from the process with ID 1 to the process with ID 2. The first step in the process switch is to perform a mode switch into kernel mode, along with a context switch to the section of the kernel that handles process switching. That component of the kernel saves the program counter and CPU registers into the process control block for process 1. Also, the process state for process 1 is set to ready, indicating that the process is ready to run again once the CPU core becomes available. The process switching code then restores the CPU register contents and program counter value from the process control block for process 2. The state of process 2 is changed from ready to running, the CPU privilege level is returned to user mode, and context is switched to process 2. Process 2 now begins executing. During the lifetime of a process, the corresponding process control block is moved between various queues in the operating system. Each queue is a linked list of process control blocks, and multiple linked lists overlap. All PCBs are at all times in the job queue, which is a linked list of all process control blocks in the system. Process control blocks corresponding to processes in the ready state are linked into the ready list. Processes waiting for device I/O have their PCBs linked into various different device queues. In this diagram, we can see the PCBs for 5 different processes. All PCBs are members of the job list, with list links depicted by the green arrows. 3 jobs are in the ready list, and 2 jobs are in a device queue waiting on I/O. The linked lists within each queue are represented by the dark blue arrows. Notice that the 2 linked lists for the queues overlap the linked list for the job list. Careful management of linked lists is a major requirement of operating system kernel code. Now I'd like to shift focus for a moment to mention scheduling, since it is closely related to the linked list management. In operating systems theory, we typically divide scheduling into 3 types: job scheduling, midterm scheduling, and CPU scheduling. Job, or long-term scheduling, refers to the selection of processes to place into the ready state. This type of scheduler has a long interval, typically on the order of seconds to minutes. One of the clearest examples of job scheduling on modern systems occurs on high-performance computational clusters, on which users submit jobs that may require hours to be scheduled and executed. Midterm scheduling refers to the swapping of inactive processes out to disk and restoring swapped processes from disk. Many of these tasks are now part of the virtual memory subsystem. CPU scheduling, or short-term scheduling, refers to the selection of processes from the ready list to run on CPU cores. This type of scheduling will be the subject of future lectures. One important operating system component related to short-term scheduling is the dispatcher, which receives a process control block from the short-term scheduler and restores the context of the process. The dispatcher also completes the context switch to the process by performing a mode switch into user mode and jumping to the instruction address specified by the newly restored program counter.
Ayun, tapos na ang ating live stream, mga kapatid. Maraming salamat sa lahat ng nagpunta at nanood. Thank you. Susunod ulit. Salamat.